everyone. Thank you very much for being here and also for joining us online. I think everyone is online. All right, great. So welcome everyone. I'm very happy to introduce this session today, this workshop today on C4 value. Basically, it's about critical raw materials from unconventional sources and explaining what we're doing in C4 value, but also with our partners and sister projects that are engaged in a similar line of work to ensure supply through circular economy, engaging novel technologies. So as you can see, my name is Hannah Abke. I'm the overall coordinator of C4 Value, but also from the technical coordinator, Sandra Casas is here. She'll be introducing the project's objectives and results so far next, I think. And also I'd like to welcome Dr. Chris Fellows, who's joining us here. He's also part of our external advisory board, so welcome. And obviously all our partners and interested stakeholders who are here, who have joined us in this meeting to exchange ideas. And I'm also looking forward particularly to the presentations by the sister projects. Before we continue, I wanted to point out that this session is going to be recorded. So everyone who's on Teams, who doesn't want to be seen, you can, keep your camera off. If you have a question, you can put it in the chat. Our colleagues are there, they're monitoring it. So any kind of question and answer session is going to be handled through chat. We don't have any other platform. Please make sure that you use that if you don't want to unmute and ask the question directly. So let me just lead you through the program for today. So after this introduction, we will have a basic overview of C4 value. The objectives and main results are, as I already said, by my colleague, Dr. Sandra Casas. And then we will have the moving lab integration by Dr. Nayara Hernandez from our partner Aqualia. So that will be also a summary of all the technologies, all the work that has gone into this project in the last 3 years. It is quite a lot, and everything is going to be bundled in a moving lab, and it's really, I'm looking forward to that presentation as well. Then Dr. Chris Fellows is going to give us an overview of the potential value of desalination brine. The multiple facets of not only obtaining critical raw materials and IPR in terms of innovative methodologies, but also gaining clean water. So I think with our technologies, I saw in the brochure there that we can make 80% of clean water, which I think is a great result. But the main focus here are the 10 minerals and metals that we want to gain to provide to the critical raw material supply in the European Commission. So after that presentation at 11:10, we'll have a break and some networking coffee, 35 minutes. So really it is a networking coffee. Then after that, we'll have the sister projects presentations, Circular Mine, Dr. Fabrizio Vicari, who is going to be presenting water mining. Dr. Guillermo Zaragoza is going to be presenting that. Live in Desal, Dr. Lucas Bardella, and Metallico, Dr. Jose Luis Cortina. So after that, after all the information has been absorbed, we go into roundtable number 1, the recovery of metals and minerals as an economic lever for desalination plants. So here we are talking about the economy, not just local or national economies, but also at the European level, and also what kind of an impact it would have on a global level. The second roundtable at 1 p.m. is going to be CRM market barriers and opportunities. So that's going to be also a very interesting one because there is, well, the European Commission demands that we don't just do projects for the fun of it, for the science, but also for the economic benefit, for the opportunities in the labor market, and obviously to also become self-sufficient in terms of CRM. And then at 13:45, there will be a closing talk by Aina Amengual, who organized this session. So also thank you to Aina and everyone at Catalan Water Partnership, CWP, sorry, for organizing this. And what I wanted to highlight is that after each roundtable, there'll be a session for question and answer. So it's not just going to be roundtable and then we go straight into the next roundtable. There'll be chances to interact and ask questions. And that's it. So with no much further ado, I introduce you Dr. Sandra Casas to lead you through the C4 Value project.
Thank you, Hannah. So good morning, everyone. Well, let me start thanking also the Catalan Water Partnership for organizing this. It's a pleasure to be here today and to explain the C4 Value and exchange with the other projects and experts on the topic. So my name is Sandra Casas. I'm the head of the water research line in Eurecat, and I'm going to explain you a bit overview of the C4 Value and the main results obtained until now. You will see that in terms of results, I will not be really explicit, and it's something that it's related to the IPs. So it's a topic that we are still discussing internally, so you will see very general results. But I hope that in the next months, you will see some more details. So starting with it, I will start with the introduction. I will show you the status of the project and a bit of a review of the solutions that we developed, and then the short summary on the results that we have obtained. So C4 Value is a research project. It's a low TRL research project, European funded. It started in 2020 and it will end later next year. And we are coordinating as Eurecat, but we have 16 partners covering all the value chain from the research, so research entities, universities around Europe, until companies, operators such as Aqualia. We have also, and the final value chain that are the market uptakers, like Omia, like Dekema, and other entities that are dealing with the final results. So our main objective here is to develop and implement disruptive technologies. That means TRL between 3 and 5, so under development, to recover minerals and metals from seawater desalination brines. Mainly, we want to change the paradigm of the desalination, and instead of throwing the brine away, we want to recover minerals and metals from these brines. So we want to apply the technologies and recover these raw materials, and not only do that, but do it with low environmental impact, so to diminish the impact of brine discharge and also the impact of the own technologies applied, and increase the water recovery from this brine. So mainly our objective is go from the traditional desalination scheme where we are recovering 50% of water and we are throwing 50% of brine, to a scheme where we are recovering 80% of water, and from the 20% brine discharge, we are recovering minerals and metals. The minerals and metals that we are focusing on are the ones that you can see here. So critical minerals and metals and strategic ones. So we are focusing on boron, magnesium, scandium, gallium, indium, lithium, vanadium, molybdenum, and rubidium. So the technologies that we are developing within the project are focused on recovering one or more of these elements. We are doing this development not in a traditional way, so we don't have a fixed scheme of treatment. So the technologies that we are developing can be placed in different places of the scheme. So it doesn't mean that that one technology is only focused on at the end, let's say, of the treatment scheme, but we can move it to another place, and we are doing the tests with different inlet characteristics, so to see how the technologies behave with different inlet brines. That means that we are proposing this multi-mineral and modular process. So we can adapt the process depending on the type of brine that we are treating. So this gives us a treatment that should be modular and flexible and effective and cost-effective, ideally. So the project is organized in different work packages, so I will not go in detail about the structure, but Mainly, we first started doing a review on what is the quality of the brine. So we collected 150 brines all over the world, and we created a brine catalog that you can check. It's in the website that you can see in the first part of the, I don't know if this, yes, here. And this gave us an idea on what were the levels of the different elements in the different brines all over the world. This helped us to start developing the technologies. So we worked with technologies for pretreatment, concentration, extraction, purification, and crystallization of these minerals and metals. For these two parts, we have already done that, at least with synthetic brines. And now the project is in the process of integrating all the technologies in a moving lab that later on Nayara from Aqualia will explain, and test it with different brines, 3 different brines at least, of different origins. Additionally, we are creating a decision support system, so a modeling tool to model the performance of the treatment, and so to be able to define this scheme for each brine that what we aim to test. And finally, at the end of the project next year, we will have to validate the cost effectiveness of the treatment and also the technical feasibility with the real brines. So the technological solutions that we are developing are mainly pretreatment, that we are focusing on nanofiltration. It's a modified nanofiltration to improve the separation of monovalent and multivalent ions. And then concentration technologies, where we are working mainly on membrane crystallization and also an advanced multi-effect distillation developed with novel materials, so to reduce the energy consumption and also the corrosion potential. And then finally, we have the selective technologies, so to recover the elements and crystallize or precipitate the elements. So we have polymeric inclusion membranes, we have electrodialysis with bipolar membranes, 3D printed absorptions, ionic liquid solvent extraction, synergetic solvent extraction, and binary extraction solvent extraction, and non-dispersive solvent extraction. So a wide range of technologies, some of them known from the metallurgic industry, and some of them novel in their own sense. So to be able to selectively recover these elements. So as main results, I'm going to the last part of the presentation. In terms of pretreatment, we have been able until now to develop a nanofiltration membrane with coated surface that has improved the rejection between monovalent and polyvalent ions. And we have obtained more than 92% rejection of magnesium with synthetic brine produced with the major ions of the solution. In terms of concentration, we have developed these thermally conductive polymer composite tubes for the advanced evaporation technology. And we have constructed an evaporator to be integrated in the moving lab, and we will test it with real brines. The idea is to evaluate this system to see really the lower energy consumption compared to conventional ones, and also the lower corrosion potential. And for membrane crystallization, which is the other technology that we are using for concentrating brines, we have been able to concentrate the brines up to 6 times and to recover magnesium with 90% purity. And finally, for the selective technologies, you see here we have developed a module for the absorption of indium, molybdenum, boron, scandium, and vanadium. And we have achieved 90% absorption efficiency, so that gives us a good concentrate to finally recover the elements elute. We have developed a process for the recovery of gallium with liquid extraction with ionic liquids with 90% recovery. Also for indium, vanadium, molybdenum, we have tested non-dispersive solvent extraction with 90% efficiency. We have recovered rubidium with 86% recovery. And finally, we have used electrodialysis followed by electrodialysis with bipolar membranes. So to concentrate the boron solution extracted from the 3D absorption modules and to recover this boric acid with 80% current efficiency and 2+5 concentration factor. Finally, we have also been able to recover lithium after 3 stages and recover 90% of lithium with precipitation with carbonates with 92% purity. So apart from these, which are the results of the technological developments, we have been working also on the modeling. So the development of a platform that will be ready at the end of the project, so to predict the performance of the technology. You will find also this model in the website once it will be ready. We have work on the moving lab that now Nayara will show. And also we have started the life cycle assessment for the technology. So to see the sustainability assessment, we have started with a market framework. We have compiled the information about the quality, quantity, and impurities that we are obtaining with the solutions. And we are starting the work for standardization of the technologies. So this is the point that the project is now. We still have 1 year ahead. So a lot of work to be done, especially because we face now the challenge part of integrate of the technologies and test it with real brines. But the results until now are quite promising. So we hope that at the end of the project, we will have a good set of solutions so to further develop in next projects. And well, that's all from my side. Thank you very much. I give the floor to Nayara Hernandez from Aqualia, that she will explain the moving lab.
Thank you, Sandra. Good morning, everyone. Well, Sandra has already explained you the overview of the project. So now I'm going to try to explain you one of the objectives of this project. That is the moving lab integration for the recovery of minerals and metals from brines. Specifically from brines produced in a seawater desalination plant, in the desalination process. So, this stream always has been considered as a waste that is commonly discharged into the sea. Well, here I would like to point out that if the discharge into the sea of this brine doesn't have a negative impact, if the discharge is done properly with diffusers and the correct distance from the coast. But the point here is that we are not taking advantage of a stream that has a high content of minerals and metals of high industrial value. Like, for example, as Sandra said, lithium, scandium, vanadium, rubidium, molybdenum, indium, gallium, magnesium, and boron. The problem is that most of these elements are present in the brine in a really low concentration, as you can see in this table. So nowadays, the recovery of these elements is not feasible. We have to do a lot of work in the development, in developing and optimizing the technology that we have for the recovery of these elements. So C4 Value has this objective, as Sandra said. All the partners from C4 Value project has been working has been working for develop technologies and optimize them for the recovery of minerals and metals from brines. Okay, and all these technologies are not gonna work separately, but in a single process. So because we want to develop a modular and flexible system to recover these elements and to be implemented in a seawater desalination plant. So this is a simple scheme of the C4 Value process. We can divide the process in 3 steps. The first one is the pretreatment step. The second one, the concentration step. And the last one, the extraction and purification step. For a process to be viable, These two steps are really important, the pretreatment step and the concentration step. So let me explain you as a bit the process for value process. We have a first step that is the calcium precipitation, where we eliminate or recover the calcium present in brines. Later, the brine free of calcium go to the next step, that is a nanofiltration system that separates the brine into streams, a multivalent rich stream and a monovalent rich stream. Then this stream go to the concentration step by means of membrane crystallization and multi-phase distillation. Once the brines is concentrated, go to the last step, that is the extraction and purification step with all the technologies that Sandra showed us before for the obtention of all these elements. All these technologies will be integrated in a container for its easy transportation and installation in different seawater desalination plants. So each technology, most of the technologies work in batch mode and treat the necessary volume of brine to fit the downstream technologies. So we will implement this moving lab in a seawater desalination plant, and we will test all the technologies in relevant environment with different brines. So well, you can see here some pictures of some of these technologies. This is the binary extract and solvent extraction for the lithium recovery. This is the advanced membrane crystallization for the concentration of the multivalent stream. And this is the calcium precipitation, the first step that we have in the C4 value process. So we will test all the technologies with different brines. But brine from where? Related to this, we, as Sandra explained before, we have created a brine composition catalog with the composition of brines around the world to identify the optimal geographic location to maximize the metal and mineral recovery from brines. So we collected almost 150 samples of brines from 35 countries to create a database to create the platform for to identify the stream that we want to test or to maximize the recovery of minerals and metals. So this is the timeline for the moving lab. We had a first task that was the moving lab design. Later, the moving lab construction. We finished the moving lab construction last month. So now we have just started the moving lab operation in the demo site selected, that is a seawater desalination plant in Tenerife operated by Aqualia in Canary Island. And there we will test all the technologies with brine from the Atlantic region. But not only with brines from the Atlantic region, but also with other brines that we selected because of its interest in the composition that we observed from the previous works. So here in this table, you can see the 3 brines that we are going to test. The first one is the brine from Tenerife, from the Atlantic Sea. The second one is another brine from Spain, but in this case from the Mediterranean Sea. And the last one is a brine from Israel. So as you can see in the table, in the case of the two brines from the Mediterranean, they contain a higher concentration of some elements like magnesium, boron, or lithium. So we expect to have really interesting results comparing all the moving lab operation with different brines. But we have just started the operation, so I hope to show you next time the result for the operation of the moving lab. And these are the impact that we expect from the project. That is a new local source of minerals and metals, a new technological solution for seawater desalination plant and also for other processes, and a map of brine composition for the European Raw Material Information System. And this is all from my side. Thank you very much.
So thank you very much, Hannah, for introducing the workshop. Also, thank you, Sandra and Nayara, for the brilliant summary of the Super Value project and its results. It is really a pleasure to have to you all here today, including those of you who are connected online. Let me introduce myself. My name is Aina Mengual. I'm a project manager at the Catalan Water Partnership, a non-profit association that operates in the sector of sustainable use of water in Catalonia. And we aim to improve the competitiveness of our members. Specifically in the C4Value project, we have the role of stakeholder engagement. So now I will present the following intervention by an international seawater mining expert. He is Christopher Fellow, senior water expert at the Saline Water Conversion Corporation in Saudi Arabia, and an adjunct professor at the University of New England in Australia. The title of his presentation is The Potential Value of Desalination Brine. The floor is yours. Cheers, Chris. Thank you.
Thank you very much, Anna. Thank you very much for the invitation to speak here today. I hope you will not be disappointed. So that's my name there coming up. So I'm from the Saline Water Conversion Corporation. So we claim to be the world's largest producer of desalinated water from the sea. So currently about 6 million cubic meters per day. You would have seen that the pie chart that Nayara showed with the large red wedge up the top for Spain and the large orange wedge down the bottom for Saudi Arabia. These are mostly our samples from our different plants on the Arabian Gulf and on the Red Sea. So my background is in physical chemistry. So I've been trained, and all my experience for many years has been in thinking quantitatively about problems, which of course can get you into trouble when you move into sectors outside of science. So I'm going to be talking about economics today, but I was told that the audience has a good background in chemistry. So I'm going to talk about economics as if it was physical chemistry. So when we talk about the value of something, we have to talk about what's there and what is it worth? And that gives us something like the Gibbs free energy economically for that particular product. But then we have to consider the particular situation. What is the market for that product as opposed to its value? So that gives us the standard Gibbs free energy. So now we've got just the regular Gibbs free energy. And then we have the problem of how difficult is it to realize this technology? What are the barriers we have to get over in terms of cost and also social, economic, social, environmental, political barriers? That's like the activation energy for that particular product. So you've probably seen figures like this before. So this has appeared in quite a few reviews over the years. So this is a version of the one that we published last year with error bars added, thanks to suggestion by John Granfield. So the published version of this doesn't have the error bars. And I apologize for all the really serious scientists out there. This is the only slide that has error bars. Just have to keep that in mind. Yeah, all the other data that I show you, you have to input the error bar in yourself, and there's a bit of variability there. So here we have the concentration down the bottom and the price on the y-axis. And if we want to find the standard Gibbs free energy economically of each of these things, we have to multiply those two things together. You've seen probably graphs of this that show the element, which can be a bit misleading. So if we take it for the element for seawater, we get this, that if we were to take seawater and convert it to oxygen and hydrogen, obviously there's a lot of value there. But you can think of many reasons why this isn't a good idea. So first of all, there's better sources for oxygen, and there's no conceivable reason that you would need this much oxygen. So we can just condense it out of the air. There's no need to electrolyze seawater to get oxygen. Green hydrogen here, this has actually become a sort of serious question, but the cost of processing water to get to something that you hydrolyze is a very small cost, very small part of the cost of producing hydrogen. So there might be cases where, getting green hydrogen from seawater makes sense. All depends on how cheap the energy is that you're pumping into the process. But we're going to discount those two and go to the things that are in the brine after we've gotten rid of the water. So this is doing that exercise, multiplying those axes together. You can see that sodium hydroxide, magnesium, hydrochloric acid are really dominating there. These are things that you actually have to put in quite a lot of downstream processing to get to. I suppose you could rearrange these elements in other ways. We're not going too far down the track of rearranging things. So we need very significant additional processes, outputs to get those top 3 products there. And one thing that this slide sort of highlights is that we're not really talking about brine mining. So this is something that Neil Moe said at a conference again last year, I think. Mining is basically taking stuff out of the ground and putting it in a pile. And once we have our brine, well, we've done the mining, we've got our brine, it's all there in a pile. What we're really doing, where all the thought and the energy has to go into it, is refining that product. So what we're really talking about is brine refining. So I'm just going to remove the ones that are a bit more complicated to get to and get to this slide here. So these are all things that we can get out of brine without having to do too many complicated things to it. And you can see that it's really dominated by the magnesium salts there. Sodium chloride, obviously important, potassium salts, bromine, and then it very rapidly tails off to things where the product of the amount that's there and the value of it becomes quite small indeed. So chopping that down to start at the rubidium chloride, we've got our strontium sulfate, our boric acid, lithium carbonate, and then very, very minor things that we get to quite quickly. So this slide here shows everything as of last week when I rechecked the prices for things on the internet that is worth more than $1 for 1,000 cubic meters of seawater. So you get all the solids in 1,000 cubic meters. This is where the value lies. Very, very dominated by magnesium. So that's as our you see the standard Gibbs free energy slide. On this one, I've taken out the things for which there really isn't a realistic market. So there's already an excess of magnesium chloride out there. You can only really sell it for use in dust control. Be hard to break into there. Calcium chloride is a byproduct of the Solvay process. There's also far more of it out there than you could ever want. Calcium sulfate, gypsum, produced very cheaply by mining all around the world, and the calcium sulfate that comes out of any conceivable brine mining process is low purity, and it comes out at a stage in the process where it's difficult to do much with. Calcium carbonate, also very many other sources. Rubidium chloride, there's not really that large a market for rubidium chloride at the moment. Similarly with strontium sulfate. So there are mined sources for those that can meet most of our potential needs. I guess in a strategic way, though, if you don't have those sources, and at the moment, almost all the rubidium is controlled by China, so rubidium does make sense as a target as it is for this project. So now let's take the main things there and put them on a free energy diagram. So we can see that the economic energy here that we can obtain from these various things, and so the top one there is the economic free energy of bromine. And those are the other major ones there. So the largest value there, so we can get things to magnesium metal or the products of the chlor-alkali industry, the sodium hydroxide and chlorine. Obviously, there's lots of useful downstream chemical processes where those will be of value. And what we think about all the time in chemistry is if processes are thermodynamically or kinetically controlled. So if it's thermodynamic, we go straight to the one that gives us the most energetic difference. But we may very frequently get a reaction where we get something that doesn't seem to be the most favored product by thermodynamics. That's because there's a smaller energy barrier to get there. So this is where we'd have the kinetic product of a process. So we have to have a look at the economic activation energies for getting to these different things. So I'm going to change metaphors now to one that's very frequent, which is the idea of low-hanging fruit. So we talk about all this, what's the low-hanging fruits? This is my brine mining tree. And you see the lowest hanging fruit is just taking brine and selling it as brine. You can find people who who want to buy that for different purposes. Like the fishing industry has some interest in taking our brine just as it is for their uses. The next lowest hanging fruit is bromine. So let me know if I start running out of time, but I'm going to spend a little bit of time talking about bromine because it really is the lowest hanging fruit if we want to extract something of value from brine, from desalination brine in particular. So the applications for bromine is in a lot of organic compounds used as flame retardants, other more exotic synthetic chemistry, biocides and water treatment. That's a shrinking part of the sector because there are better biocides and better water treatments. And one that's growing, particularly in the part of the world that I'm working in now, and where we have a lot of interest in, which is bromide-containing chemicals for oil fields, for extracting the last little bit of oil out of those formations. So where bromine comes from in the world is really quite concentrated. It's not as concentrated as a lot of rare earths that are just coming from China, but you can still see that the supply chains are potentially under a bit of threat there. We've got a very large amount coming from the Dead Sea on both sides. We've got a large amount coming from underground brines in the United States, and we've got a bit of more scattered distribution around the world from other underground brines. The Chinese ones have a low bromide content and are being depleted, and then bitterns from salt works around the world. So after you've got the salt out of your solar salt manufacture, the bitterns that are left over are good sources of bromine. So you've got your bromide there. I got a few chemical formula in here as well. We just have to oxidize the bromide somehow to bromine there. So we got, and then distill that. And so through something like this. And historically, bromine was produced directly from seawater. So this was the first real seawater mining that was done. So initial work was done in the 30s, and it grew rapidly through the 20th century. The main market for bromine was for making tetraethyl lead, though, in unleaded petrol. So the bromine industry did collapse and people stopped making it from the sea. So if you make it from the sea, you have to take a slightly more complicated approach to it than simply taking your oxidized solution and steaming out the bromine. You have to blow the bromine out and then absorb it on something. So this is one way to do it. The first one was this alkali absorption process. So your alkali reacts with the bromine, converts it to something else that again you've got to treat to get the bromine out of, and then you do the steam distillation. This is another way to get there. With did you want to see it? Take a picture? Okay, that's all right. With absorption with sulfur dioxide, and this is all technology that was really developed a long time ago. So in the 1940s, they were doing this, and we don't need to see that. This is a plant that was producing bromine from 2 million cubic meters a day of seawater. So started out in the 1940s, operated until 2003 when it became uneconomic to run this plant anymore. This is in Wales, off on the Isle of Anglesey, just up in the Irish Sea. And if we compare what they were doing in 2003, and they were making money from this pretty reasonably until the Dead Sea took over, and what we can do with desalination brines now, we have a number of advantages. So comparing Amlwch to Ras Al Khair, which is one of our big desalination plants on the Arabian Gulf, our brine is coming out with 65,000 ppm plus total dissolved solids. So that corresponds to a much higher bromide content than the approximately 34,000 ppm seawater in the Irish Sea. It's at a nice temperature to operate with all year round. At Amlwch, they operated at half capacity through the winter because the water was too cold. So that's a big bonus. And they had to treat the seawater coming in before they could do all these things to it. We're taking brine that's already been pre-treated. It's a byproduct of the desalination process. So this is something that makes sense. this is another reason it makes sense. So as well as the political situation in this part of the world, the Dead Sea is a finite resource, and we're getting rid of it pretty quickly. You see it shrinking away there. So there are established technologies for making bromine, very clear benefits for desalination brine over seawater. So quite a low activation energy for getting to bromine. The brine that we produce, our company, could meet the world needs for bromine. So potential for some disruption to the market. So the other thing I wanted to say here, just thought of now. No, well, if it comes to me, I'll come back to bromine later. So that's it. So the other thing is you can actually do the experiment in economics as well. You can put out a call to say, we've got some brine companies out there. What can you do with it? And so this is an experiment that we tried, and the people that came back with serious proposals were mostly interested in bromine. Hopefully that's not a secret, so I don't get in trouble for saying that. So that's bromine. Next, in terms of activation energy, is sodium chloride. So getting sodium chloride from the sea is ancient technology. You've all seen Gandhi doing it about 100 years ago. Today, it produces about 100 million tons per annum, which is about 1/3 of the sodium chloride used in the world, comes from the sea. And so this is where it's produced around the world. So lots in India, lots in China. Very significantly, there are big production on the coast of Western Australia and in Baja California, which is producing sodium chloride, which is used industrially in Japan. So you can produce sodium chloride by a solar process and not just use it locally. You can ship this relatively low value material right across the Pacific Ocean and make money doing that. So comparing seawater and desalination brine as sources for sodium chloride, we're starting off in a much better place than conventional solar salt producers. We've already removed a lot of the water because we want the water. So we need a much smaller land area if we're just going to go with really regular, boring, ordinary old solar salt production. And so we're obviously also at a better starting point for all the things that you can get downstream from the bitterns. If we wanted to extract bromine from the bitterns instead of going directly from the desalination brine, obviously that would be even more economically beneficial. And there are other salts that come out there, potassium salts and magnesium salts, just through a conventional solar salt production. Obviously, if you put in a little bit more effort, so nanofiltration was one of the things that's already been mentioned. If we put in nanofiltration, we can get a much purer product just by very conventional technologies, treating that monovalent brine stream that comes out. And something that we are very, very interested in, we've put a lot of effort in, is membrane brine concentration. So you would have seen multiple effect distillation as a means of concentrating the monovalent brine in Nayar's presentation. So in the desalination world, we've moved right away from thermal technologies as much as we can, because in general, they have a higher energy footprint than membrane-based technologies. So we now believe, we don't just believe, we have experimental evidence that we can concentrate brine using membrane-based technologies down to about 220,000 parts per million, more cheaply, using less energy than we could if we used thermal technology. So the challenge is to see how much further we can push that, what greater concentration we can get to with membrane brine concentration. So more of an activation energy, because there's a lot of people doing this, a lot of people making salt out there. There are definite benefits in terms of the purity of the salt that you can get if you apply the nanofiltration. And we're obviously starting with a higher concentration, much smaller land footprint. But the problem with the smaller land footprint is that you usually have desalination plants sited either next to the urban area that you want to serve. So you want to produce water for an urban area nearby. So there's not a lot of cheap land that you can establish a solar salt plant. So the goal here is to get the footprint down small enough with other technologies that allow us to get the water out. So the membrane-based technology, we can sell that water as well, so that we don't need all that land for the conventional salt processing. So that's the challenge, but because we can't just go straight out and use the established technologies. Next is magnesium. Yes, yeah, water would be great. Should check what we're going with the time here. So magnesium is another. Thank you very much. Magnesium is another product, another element that has historically been produced from seawater. Also, going back to Dow and to I think even before the 1930s now. By multiple stages that require a lot of chemical inputs. So first of all, precipitating with some base to give magnesium hydroxide, and then, well, you've got to traditionally dry this magnesium hydroxide to get magnesium oxide, then react that with hydrochloric acid, then dry that magnesium chloride, and then electrolyze that magnesium chloride. So lots of energetic inputs, lots of chemical inputs to this process. So this is what they did. Actually, really reacted the magnesium at their big plant in Freeport, Texas, not with lime, but with dolime. So this is produced by calcination of dolomite. So putting some magnesium into the process there as well. So you would expect, we've talked about how energy intensive this process is. You'd expect it to be replaced as civilization progressed with a less energy intensive, less polluting process. But unfortunately, that's not what's happened. So during the 1990s, when we were all very concerned about, starting to become very concerned about environmental issues and the growing threat of anthropogenic global warming, a couple of unfortunate things happened environmentally. So this is a big slab of Brazil here in northern Mato Grosso, I think, before the 90s. And then after the 90s, that's a bit of Europe on the same scale there. So tremendous deforestation. But another bad thing that happened was that the Dow process was replaced by the pigeon process as the main source of magnesium. So this is even more energy intensive and polluting than the Dow process, but it made sense in terms of the economic thermodynamics, so to speak. So the Chinese could do this very cheaply. It didn't involve as much intellectual know-how. It didn't involve as very large scale facilities to make magnesium in this way. So you see this has an intrinsic carbon footprint, not just by getting rid of the carbon dioxide from the magnesite to get the magnesium oxide, but from making all this ferrosilicon that they use on the reduction step. So independent of all the energy that's going into that, we're pumping a lot of CO2 into this process, and this took over sort of coming from the mid 90s in a very short amount of time, just because it was much cheaper. This is showing just how bad it is. So magnesium, very energy and carbon intensive, pretty much whatever process we do, unfortunately, but the pigeon process significantly worse than the electrolytic process. And contributing to things like this. So that purple area in Liaoning, a lot of that came from magnesium production. So one of the hopes for the world for magnesium being produced by other ways is that Chinese authorities are actually cracking down on a lot of these environmental problems. So magnesium producers have been shut down, which opens a door. So how far is that door open? So we know desalination brine has a clear advantage over seawater for making bromine from, has significant advantage, a clear advantage for making sodium chloride. With magnesium, using the Dow pathway, it's rather more obscure. So handling a smaller volume isn't really a great benefit. You still have to use the same stoichiometric amount of chemicals in there if you're going to produce magnesium by this process. And the base you use, any base has some problems. So sodium hydroxide's expensive, especially in our part of the world. It's nearly as expensive as the magnesium hydroxide that we would get out. If we use lime, that has an intrinsic carbon footprint to get to that lime. Potentially we could use green ammonia as a source, but then there are complexities that arise if we get ammonium in our product. So we have no great advantage from having it more concentrated. We have the same challenges of separating out the phases that you would if you were precipitating it from seawater. You get the same problems with precipitation of contaminants like calcium sulfate coming into your product. So it's not clear what competitive advantage desalination and brine has here. And please correct me if I'm wrong, but I don't think anyone is doing this commercially in the world at the moment to make magnesium. So there are obviously real benefits to getting magnesium from seawater, as well as this huge economic free energy, as we've seen. Environmentally, it's going to be so much better if we can find in competition to the pigeon process, and we have a nigh infinite source. We're not relying on magnesite deposits that are mostly up there in China and North Korea. But we have this competing bit of our diagram here. So the economic thermodynamics are against us, and we really need new disruptive technologies to make this possible. So we need some way to get away from this process of going through magnesium hydroxide and putting all that energy in. So I'll get back to that at the end, but just briefly say a few words about everything else on the free energy diagram. With our technologies that we have now, removing them directly from the brine isn't really an option. With the volumes that you have to handle, as opposed to the amount of product that you get out, that's just going to be a very high activation energy. But if we have a process that's economic for producing sodium chloride, if we have a market for sodium chloride, what's left over is much more concentrated, and that makes those other things potentially possible. So that process of making sodium chloride, identifying the market for sodium chloride, is the rate determining step for cost-effective brine mining. Just talk about a few things here. If we have just conventional solar salt production, what crystallizes out a little bit further down is carnallite, so a mixed salt of potassium and magnesium, and this is a economically viable way, if you have plenty of carnallite from your plant, to get to potassium fertilizer. And not everywhere in the world, but still in Kazakhstan and Russia, magnesium chloride from carnallite is the principal source to get to magnesium there. So a small part of the world's magnesium market is getting there through these sort of salts. That's everything sort of put together on one diagram there, with all the barriers and various things happen. So what do we do if we have an activation energy that's too high? Anyone? Use a catalyst. Yes, yeah, we use a catalyst. So we need to find a economic catalyst to get over some of these barriers, and nanofiltration is really very significant in that regard. So what we do with nanofiltration is we separate our brine into two streams, one which has polyvalent salts, one which has principally the monovalent salts. These membranes are getting better all the time. So there are lots of companies out there with an interest in selective nanofiltration membranes. They're improving their performance all the time. If we do this, it's easier to concentrate the separate streams, and it's easier to apply potentially disruptive technologies like the ones we heard about earlier to those separate streams. So things like the bipolar electrodialysis, things like selective absorption, two things that I don't think were mentioned, but we're interested in. If you haven't heard about these, you should look them up. Switchable solvent fractional precipitation and eutectic freeze crystallization. So wherever you've got a simpler mixture, if you apply one of these potentially disruptive technologies, it's gonna be easier to apply it to the simpler mixture. So looking at the monovalent stream of desalination brine in particular, as I said, we're putting a lot of effort into membrane brine concentration, which both reduces the footprint and improves the purity as opposed to conventional solar pond precipitation. If we are doing this to the monovalent stream as opposed to seawater as a whole, we can get directly to potassium chloride rather than going through carnallite. So a lot of energy involved in thermally decomposing carnallite to potassium chloride. There's a huge market for potassium chloride. So in terms of the fertilizer market, it's vastly larger than the magnesium market. Saudi Arabia at the moment imports 100% of its potassium fertilizer. So this is like the next step along for us after we've gotten the sodium chloride, the bromine. Potentially we're doing something with the magnesium, but on the monovalent side, we know we've got a market for the potassium chloride. And then after you take out the potassium chloride, you've got a more concentrated residue again. So you're going down to a very small percentage of the brine you started with. If you haven't lost too much of your other things, just as film sticking to the surface of the salts that you're taking out, you've got something that might potentially be economically viable for these smaller things like rubidium or lithium. The divalent stream, on the other hand, we've got our magnesium there. We've got also all of the scale-forming salts. So that's a benefit for the monovalent side. Looks like it's bad for the divalent side, but this does mean we can take out all the calcium sulfate in the first stage of sequential precipitation. And the sequential precipitation is a lot simpler without so much of the other things there. We do get sodium chloride because it's impossible to get all the sodium chloride out just by nanofiltration. If we need to get out all those sodium chloride, there's other things we can do that involve extra processes, extra energy, but we typically see a sequential precipitation, sodium chloride, magnesium sulfate. It's a very significant fertilizer as well. We've identified markets there. We know we can sell magnesium sulfate. And then we end up with magnesium chloride at the end. And with that magnesium chloride, we know there's still a lot of value there. Oops, there. Pressing too many buttons at the same time. Without some technological advance, getting there through the DAO process is, it just seems very unlikely to me. We could, but there are benefits to get the magnesium chloride this way, as opposed to the conventional DAO process. I don't think the DAO process, just as it is, sorry, I've gotten totally confused here. Anyway, we've got magnesium chloride. Potentially, that's a source for electrolytic magnesium, and electrolytic magnesium could, in principle, have net zero, because we could get our electrical energy from green sources, from renewable sources. So as opposed to the DAO process and any other carbothermic process. So this is our vision at the moment. This is the sort of stage one of this. We have costed within the SWCC. We've got all the engineering done. We are hoping once we have convinced our off-takers that we've got material of the quality they want, they take, they've got a high bar for being convinced. We want to produce 2 million tons per annum of sodium chloride for the chlor-alkali industry locally on the Arabian Gulf, and also extract the bromine from that process. And then further downstream, we hope to add these other processes producing potassium chloride from the monovalent stream and producing magnesium sulfate from the divalent stream. And if we can make the right connections, find the right technology, hopefully make magnesium as well from the divalent stream. Something that's also been mentioned, this increases the freshwater production as well. We do this. So the summary of my talk is that while everything's there, everything comes at a cost. You can't escape the laws of thermodynamics. I think Einstein said, that everything else is subject to change. But the laws of thermodynamics, we know we're pretty solid on those. So the economic laws of thermodynamics are the same. Magnesium is where the main game really is. So everything else is small potatoes compared to magnesium. Low energy technologies for separation are very important, and low energy technologies for concentration are very important. So thank you very much for your attention, everyone. And it looks like I've left a little bit of time for questions.
Yeah, of course. Anyone have any questions? I will.
Chris Garciadis, Brine Innovation Manager with Worley for the NEOM project. I'm not quite convinced about, if you go back to your process flow scheme, that if we take out the calcium sulfate, that there will be enough sulfates to formulate the fertilizers downstream. So we had this discussion also with the same salt specialists that we have been talking, and because we had the idea of softening the polyvalent stream, yeah, but we would rather do it as calcium carbonate in order not to harm the amount of sulfates. Yeah, and minimize the fertilizer formulation downstream.
Yeah, so this is not softening. This is not adding anything to the process. This is just the calcium sulfate that crashes out by itself. So yes, that sulfate that we're losing, that's not saleable sulfate as magnesium sulfate, but we have to follow the physics. You have to follow the thermodynamics of physics. So we've lost some of the sulfate, but the balance is there. We know if you just concentrate seawater, you get to magnesium sulfate after calcium sulfate, and with the volumes that are involved, that's a lot of magnesium sulfate that we know we can make.
Okay, understood. Thank you very much.
Jose Luis Cortina from Polytechnic UPC here. We are close to the campus. It was an amusing presentation. I like very much from university professor for students. The first part of your lecture, I also like to play with all these issues of science and technology. Now, my question is, look into this general scheme. You know, you were questioning, for example, if is any reasonable attempt to recover rubidium chloride. You know, I'm also just seeing that you are not including lithium, because I think there are some large projects in Japan 10 years back that they demonstrated that lithium recovery from seawater and from brines is really challenging, no? And what is for me surprising is those also those routes of recovering potassium salts, because the potassium content in the brines are not so big numbers. No, it is true that, for example, potassium is a problem. You are not postulating, for example, the production of sodium hydroxide, and when sodium hydroxide is produced from seawater, it's a big problem that is having potassium. Then my question is why? Because one of the salts with the higher economic value is sodium hydroxide, and then why you are not postulating the production of sodium hydroxide? Because at the end, if you are separating, let's say, potassium chloride, maybe the sodium hydroxide that you will produce will having a large potential market value because of this fact. That's my question.
Yes, so I talked about sodium hydroxide at the beginning, and then decided, oh, we'll talk about that as a downstream product. So if you're in a position to do everything yourself in an integrated facility, if you have the knowledge and the technology to do chlor-alkali production integrated with your desalination plant, then yes, that makes sense. But you have to go through the sodium chloride first, and then once you've got to crystallize out the sodium chloride. If you could just use the brine directly, it would be a lot easier. But as you said, there's a lot of problems when we try to do that for the chlor-alkali process. So once you've taken the sodium chloride out, what you've got left is a reasonably good potassium source. So that's about 50-50 sodium chloride, potassium chloride. So that's why that's something that's made possible by the other stages of the process. So I hope that answered your question.
But my question is, for example, looking all this project that you are doing in Saudi Arabia, it is well described the market potential for production of sodium chloride. I wonder if you have never analyzed the market potential for production of sodium hydroxide in seawater desalination plant.
Okay, I guess we're coming from the position where all the knowledge about the technology, all the knowledge about the process is there with the chlor-alkali producers, and we're in a privileged position, so to speak, in that we're quite close to large chlor-alkali producers. So it makes a lot more sense for us to make salt that meets their requirements and sell it onto them. So yeah, there's more value that we could capture, but the activation energy is a lot higher because we would need the land, we would need the larger capital investment, we need to develop the expertise ourselves, and that to us, or to our organization, that's sort of prohibitive. We'd rather go for the lower hanging sodium chloride fruit.
Any question more? So thank you very much, Chris, for your nice presentation.
Thank you very much.
You have certainly highlighted the potential of brine to provide the world with critical raw materials. And now it's time to the coffee break networking. So let's go, and then we will move on the presentation of 4 European projects. So if you could go to your chairs, please. We'll start the next part of the workshop. Ahora sí, ahora te- I hope this networking break has been very fruitful. We will now move on the presentation of 4 European projects related with the improvement of water mining and extraction of critical raw materials from unconventional sources. These are circular mine, water mining, life in the sal, and metallico. We will start with the presentation of circular mine with Fabrizio Vicari, Innovation Manager of Resources, whenever you want.
Thank you so much, Aina, for the introduction. And thank you so much for the invitation to this nice event. So since time is very short, I've been told to be very quick. I will go straight to the point. And I'm would like to thank Chris for the nice presentation and somewhat that I can introduce our discussion. So we've been talking about desalination brines and the activation energy that brings you to the production of the other elements apart from the low-hanging fruits. So you have these low-hanging fruits, sodium chloride, calcium sulfate, bromine, which are there. They have already markets which are very stable and flat. And accessing those markets might be really challenging. So, or you try to fight against the players of those markets, or you can do as we decided to do, to ally with them. So our concept was not to fight against saltworks, but to rather give them desalination brines in order to increase their production. Or they could decrease the surface area that they have in this moment. So saltwork owners will keep doing what they can do really well, which is sodium chloride production, and also getting rid of calcium sulfate and calcium carbonate, which we don't want because don't have that much value. And then they can also perform those bromine extraction in which they are already playing a little. After that, what it is left is the interesting part. We have a solution which is rich in minerals, first of all, magnesium, and then we start extracting it. In a sequence, we will also extract lithium and the other trace element. After that, you're always going to have some sodium chloride there. And then you can produce the alkali and acid solution that you need in the extraction process. If there is any salinity gradient left with respect to the seawater, and it might be because this solution is from 25 to 50 times more concentrated than seawater, then you can also produce some salinity gradient power. At the end, you can close the circle back. And that's the circular mine concept. A concept which was first patented and then proposed to the European Commission in order to be founded. And the University of Palermo has gathered a very good consortium of 12 partners in the Mediterranean area and obtained a 6 million funding. We are now almost finished. We are not going to ask for any extension because we reached every single milestone that we wanted to achieve. And in this moment, we have built the first integrated prototype for the extraction of minerals from seawater bitters. How we did that? As we have seen for the C4 Value project, first of all, you need to know your resource. So we have created a network of 25 saltworks in the Mediterranean area, obtained their bittern, and then analyzed them. We have also performed some standardization, some internal standardization, because analyzing very concentrated ionic solution might be challenging. And we have planted a special laboratory there in the site, in the Trapani Saltworks. After that, knowing what was there, we started extracting one by one the elements of interest, starting with lithium, but then also strontium, cobalt, and gallium, and germanium. But most magnesium in the form of magnesium hydroxide. We've been practicing magnesium hydroxide extraction a lot, and we are now in that place in which we can tune the extraction, trying to have a larger aggregate, which not so well shaped, but that can be easily settled, filtered, and separated. Or on the other hand, larger hexagonal platelets in order to try to serve different markets to which the magnesium hydroxide can be proposed. And this is the reactor that gathers the knowledge that we have acquired in this period. The first version, we are now at the second version. Then, in the meanwhile, we also developed, thanks to the collaboration of our Portuguese partner, IBT, the device, the electrochemical device for the extraction of lithium, which uses novel fluid electrodes made of carbon slurry and selective membranes, which can get a really high selectivity when compared to the other salt present in the solution. Then our excellent partner from UPC, José Luis, can testify that we have been spending a lot of time also trying to understand which ion exchange resin that were already present in the market could well extract those cesium, rubidium, and trace elements that we were looking for. And that was a really intense period, but it is good to start from something that it is already commercially available, because then you can think about constructing a real pilot plant. But in the meanwhile, we also try to formulate specific resins with the help of VTT and the University of Helsinki. And this is the result. All the technologies that you have seen up to this moment are now assembled in a fully integrated prototype at the University of Palermo premises. And last week, we started the production chain, producing the first samples of magnesium hydroxide with the second generation reactor that you can see here. Here you can see the DBM. This is the skid from UPC for the extraction of strontium. Here today, we also have the MVC. So first of all, magnesium hydroxide, the value in bit terms. This is something very similar to the slide shown by Chris, but we don't have the first bars because the saltwork owners already get rid of that. Also, calcium is not here. We have less than 400 ppm of calcium residual in the bittern. So it belongs to the list of critical raw materials. Here we can start a discussion what it is really about in the list of critical raw materials. But what we have assessed is the magnesium hydroxide market itself. And we know that using our network, we could cover 80% of the total demand of magnesium hydroxide, not the metal one. Then if we extend this kind of thinking to the other elements on a global scale, we can meet the request of the strontium market with a 5% contribution to the global demand, or in money, $92 million per year. And this is relevant from the economic point of view, but also in the perspective of electrification, because we need strontium to build the magnets that are useful for building electric motors and pushing our trains in the future. Then we also have germanium, cobalt, and gallium, which are there, and that can also be produced in amount which are just one order of magnitude less than what it is the global actual production. And these are very important elements because they are strategic in the production of electronics, but also PV panels. Now we have germanium PV panels flying over our heads in the International Space Station. And that was a very quick overview of our project. And thank you for your attention.
In fact, a very interesting presentation with a lot of similarities with the Super Value project. Thank you, Fabrizio, for your presentation. Now it's the turn of Guillermo Zaragoza, Head of Solar Thermal Application at CIEMAT, Plataforma Solar de Almería, to present the progress and results of the water mining project. So,
hello, good morning. Well, thank you for inviting me to present the water mining project here. It's a large project, so plenty of information, but I'll go straight to the point. Well, this is some general information on the project. It's coordinated by TU Delft, and there are plenty of partners. And okay, the concept is that we consider water the whole value chain of water. So it's water as a resource, water as a consumable, and water as a durable. And okay, in the first case is the sea mining concept, the sea mining leg of the project. That is what I will focus on this context today, because it's more related to the previous projects that we've seen. But there's also, if we consider water as a consumable, we have the urban mining case studies, 3 case studies, and water as a durable, we have an industrial mining case study. So I will focus on the sea mining case study, one in Italy, another in Spain, but there are also the urban mining case studies and the industrial mining case studies. Okay, so the sea mining is one in Lampedusa and one in Plataforma Solar de Almería. They're very similar. It's the same concept of zero liquid discharge seawater desalination. The main difference is that in Lampedusa they use waste heat from a power plant, and in Almería we use solar energy. And then the demos themselves, in Italy is more focused on the chemistry, and in Spain we're more focused on the demonstration of the energy concept. So in Lampedusa, this is well, probably there are better slides. The core technology for desalination is MED. And the reason for that, and this is in Almería, the Plataforma Solar. The reason of using MED is because we want to use solar energy, and then and also concentrate the brine. So if we used reverse osmosis, we would need a brine concentration after that. But if you use reverse osmosis with solar energy, we need to use batteries, which are very expensive. So the benefit of using thermal desalination with solar energy is that you can store solar energy, solar heat, very easily and much cheaper than electricity in batteries. Okay, about the urban mining case studies, the goal is, I will just show the objective, which is recovering Caumera, Nereida gamma and phosphates from urban wastewater with a portable demo in Utrecht and Faro. Then another in Larnaca is recovering phosphorus and water fit for purpose. And in La Llagosta, close to here, energy recovery and again phosphorus recovery. And in industrial mining case studies, zero liquid discharge desalination with waste heat integration and chlorine. They get chlorine. Okay, straight to the sea mining case studies. So the chemistry is here. We have the seawater, nanofiltration, then the retentate from nanofiltration goes to a multiple feed plug flow reactor to get magnesium hydroxide and calcium hydroxide. Then with electrodialysis with bipolar membranes, this sodium hydroxide and hydrochloric acid. And the permeate, free of scalants, goes to the MED that can have very high recovery and then leave the brine ready for the evaporation or crystallization. In the case of Lampedusa, they're using evaporating ponds to get high quality sodium chloride. The energy source here is waste heat. Okay, there are some photographs here of the plants, the nanofiltration, the multiple feed plug flow reactor, the EDBM, and the evaporation ponds. Okay, this is the same as before. At Plataforma Solar de Almería, we're in the desert. We had to bring 300 cubic meters of seawater to our research site. And the technology, we have a 14 effect MED plant, which is very efficient. It has a thermal consumption less than 100 kilowatt hour of heat at low temperature, but working at higher temperature and with higher concentration, the aim was to decrease that to 25 kilowatts hour, not electricity, talking about heat at 80 degrees. No, less. Yeah, well, yeah, 80, 90 degrees. And it's powered by thermal energy. The concept is that it will use waste heat from a CSP plant, but this is very large. So we are using stationary field of solar collectors working at less than 100 degrees. But the idea is that on a large scale, which is when MED plants have a meaning, it will be coupled to a CSP plant. Then the seawater through the nanofiltration, this is the same as in Lampedusa, but we don't have so the idea is to decrease from 25 kilowatts thermal. We don't have, we're not demonstrating the salt extraction because it's already done in Italy. So what we do here is try to blend a part of the reject, see if it can be blended with the permeate from the MED plant and from the thermal crystallizer that produces the sodium chloride for irrigation for the farmers, because then they're using all the divalent salts that are fertilizers. But of course, that's just a part of the nano reject. The bulk of the nanofiltration reject is to be valorized to get magnesium hydroxide, calcium hydroxide, and all that. And the results so far, we get here, we can operate 100% with solar energy, and the products extracted are here, very high quality, especially for the sodium chloride and the magnesium, not so much for the calcium hydroxide. But okay, this is still work in progress. And well, some results of the urban mining case studies. These are the targets, but as I said, we're not focusing on this today. And thank you very much.
So thank you very much, Guillermo, for your nice presentation. Very interesting project that investigate water mining in 3 different streams. And we continue with the Life in the Salt project. We will be presented by Luca Sarbella, project manager at Acciona.
To all of you for being here, and so for C4Value for inviting us to this interesting workshop. So I will be presenting the Life in the Salt project, increasing sustainability of desalination by a reverse osmosis novel approach and energy resource recovery from brines. This is the content of the presentation. Well, we can go quickly through the background because here I think all of us are aware about the water scarcity we are facing nowadays. So we need new resources from fresh water, and of course, seawater desalination is one of the main source of fresh water production. However, even though the system is highly efficient, has a lot of benefits, there is still room for improvement to reduce even more some of the environmental impacts and increasing the efficiency of the seawater reverse osmosis desalination. So this is the framework where the Life in the Salt project came in with the aim of improving efficiency and the circularity, which is very important also to the sustainable development goals of seawater desalination. And the idea is to do it with a novel integrated approach. So this is a brief overview of the project. Acciona is coordinating, and then we are working together with other 4 entities. So Apria, Redstack, University of Cantabria, and Revolve. The demonstration site will be in southeast of Spain, and the project has a duration of 4 years with a budget of approx 3 million euros. So as I said, the main objective is to increase to make actually the desalination process more sustainable and more circular. So by this diagram, we can have a look at the main idea of the project, which is mostly divided into 3 different axes. The first one is to increase the energy efficiency of the desalination process. The second one is to generate renewable energies. So we touch now the brines, which was the main topic of the previous talk we have heard. And then also we have heard about this a little bit to transform brines into chemicals. So how we pretend to do to achieve such objectives with these three different technologies. So the first one is it's called low pressure multi-stage reverse osmosis, so LMSRO, which starts from the idea of a multi-stage system with where the conventional pressure vessels are shorter than the conventional one with 7 or 8 elements, and it's a multi-stage, so there is a booster pump in between which can be tuned in order to optimize the energy consumption. This system also has the two other important features. Can allow for a better flux balancing between stages, as well as the possibility to optimize the clean in place procedures. So the second axis of this project is the reverse electrodialysis, the RID, which in the context of the current project, or how we are going to implement this system, it has the benefit of being logistically easy, presenting a relatively low biofouling potential, and also give the advantage or the opportunity to take advantage, sorry for repeating, the highly salinity gradients that we are having available in the salination plants. And finally, the third point, which is a technology which has already been shown from some of the previous presentation, the electrodialysis with bipolar membrane, the EDBM, which is associated to the, let's say, the goal of transforming brines into chemicals. And indeed, this technology can produce acid and base in situ, and also, as a consequence, it can satisfy the requirement for SIP and also for boron removal in the second pass with the pH adjustment. So a very simplified scheme of the process. We can see there is like the intake of seawater goes through the pre-treatments, and then there are the three main core technologies, which each of them is associated with a specific output, energy, chemicals, and high quality fresh water. And therefore, each of these technology allow to reach one of the main objectives, so which was energy consumption, renewable energy production, and satisfy the requirement for sodium hydroxide and chlorhydric acid for the LMSRO operation. So we don't have still current results as numbers, but because we are finalizing the construction process. So this three technology will be implemented in a modular system composed by two containers, one a bigger and the smaller one on top of it, on the previous. The bottom container will host the LMSRO system, while the upper one will contain the RID and EDBM. So the three technologies will be interconnected between them, and the influent flow rates of the whole system, which is the influent will be treated by the LMSRO, is 10 cubic meters per hour. This system has been designed in order to be operated in different conditions, and the plan is to operate this pilot for 2 years. So as I said, we don't have actual numbers because this pilot is currently under construction, even though the process is finalizing. So you can see the interior parts, so the pre-treatment. Here you can see the first, second stage, and second pass LMSRO. And in the last is like one of the biggest achievements milestone of so far is to finalizing the construction of the pilot. The commissioning date is foreseen for the beginning of next year. Once the commissioning will be done in San Pedro del Pinatar, where we have the lead facilities, where we experiment our innovation technologies. So finally concluding the expected results for this technology, comparing it with conventional two-pass seawater reverse osmosis full scale, are to reduce the specific energy consumption up to 0.2 kilowatt hours per cubic meter, to generate up to 0.1 kilowatt hours per cubic meter of renewable energies, and to satisfy the whole requirements of for sodium hydroxide and chlorhydric acid. Finally, the idea is that the integrated solution can transform the desalination plants into sustainable and resource-efficient plants producing high-quality water, energy, and commodities. So I would like to thank the consortium and all entities involved in the project, and also the entities who organized this workshop today. Thanks.
Luca, a project that will allow to make the desalination processes more sustainable and circular. Thank you for your presentation. Now we are finishing with the last project. It has a different objective, but we'll learn a lot with the presentation of the Pendálico project with José Luis Cortina, chemical engineering professor at the Barcelona Tech UPC.
Okay, thanks, Aina. It is true there are not brines, but there are the starting point are raw materials that are characterized by like brines, because the elements that you want to recover at very, very low levels. This project was funded in the last year in the school of the CL4 in the Resilience 0.1. Is a project that was funded by close to 13 million euros, and is mainly devoted to recover metals that are associated to the electrical vehicle batteries from both primary and secondary resources. And it is true that, is especially when working with primary and secondary resources for those elements in Europe, for example, is a very, very huge social pressure. There is the biggest one mine in Serbia is not open because of the pressure, and the second biggest mine probably will be in Spain. Is not open, and then the project was allocating, let's say, too much effort just on this social accepted, and also the real ones that are the techno-economical feasibility of the process to be developed. Then is a project where they have selected 5 different case studies. It's an innovation action, and then we need to reach technology readiness level between 6 to 7, and 4 potential replication cases. And it was selected for the project these 5 elements: lithium, cobalt, manganese, nickel, and copper. When we started the project, according to the critical raw materials list, only we have cobalt and lithium as a critical raw material elements. But in the last list that was published in 2023, remember that additionally to the critical, they had defined also that an element could be strategic, and then copper, nickel, and manganese they have included in the new list that it was released in 2023. Is a project that is, I can understand why it was approved. It's a large number of Spanish members, but we have 3 mines involved from the 4 case studies or sites. 3 of them are seated in Spain. And after we have one site case that is in Poland, and also we have other, let's say, one demonstration case that is in Greece, and after we have partners from all over Europe, mainly Germany and Finland. And we substitute in the past, it was Omnia was included, but it was a change that you just discard to continue, and now this company that is called Barbot. Okay, I will explain, summarize, because we started January the 1st. We are going to have the first year of the project in 3 weeks here in Barcelona. I will try to explain what is expected in each of the cases. Okay, the first case is in Cobre Las Cruces. Cobre Las Cruces is a mine producing copper from one mineral that is going to be is already over, and then there are processing some tailings. And then this is the telco process, and basically is to develop a scheme where after recovering copper, there is a very, very acidic stream of sulfuric acid, and is containing not too much, no high content of cobalt. And then we need to develop a processing stage where using nanofiltration, operating at very, very acidic conditions to recover the acid and to concentrate the cobalt after to just to recover the cobalt and as a metallic cobalt probably, if not as a cobalt oxide. And then there is always one company, in this case, is Glencore or Nikkelverk in Norway, or Finland, to validate the suitability of this material. Okay, but Atlantic Copper is building what is going to be the new facility. The new facility is called a polymetallic factory, where additionally to copper, they will recover copper. Sorry, additionally to copper, they will recover zinc and lead. But these streams, after recovering copper, zinc and lead, it will be a stream is having some large amount of manganese and calcium and sulfate, and values of cobalt where it's not possible to apply solvent extraction. And then we need to develop all the purification and concentration stage to just remove all this interference, just to produce copper sulfate grade to be used for the companies that are producing or they are using those for the production of anodes for the batteries production. And then there is these companies involved on the validation of the product quality of the materials produced. Okay, the third case is with Tarsis Mine. Tarsis Mine was over many decades producing sulfuric acid from pyrite, and they were discarding the mineral that was having a high content of metals, because they were only interested in producing sulfuric acid. And now the project is starting just trying to process all the tailings. They were rich on metals. And in this case, the two elements of interest are cobalt and manganese. This is a project where we are starting from the mineral, and then it's a very, very intensive work on the mineral processing stages for analyzing mineral liberation and mineral concentration by using flotation. And after that, the typical leaching stages, just to see if it is possible to recover some mixture some metal sulfides, nickel, copper, and cobalt sulfides, or just to produce the hydroxide forms as a potential solution, because most of the formulations for batteries, for cathodes in batteries, are accumulating a mixture of these elements. And then also it will be Glencore just taking part of the validation of the materials to be used. And finally, there is one case study devoted to the recovery of lithium from one mine that is going to be expected to be open in Spain maybe in a few years. The typical problem of when you are processing lithium minerals, all these very, very famous minerals where you have lithium, is typically before the leaching stage, you need to put the mineral in a furnace to 900 degrees to make a change in the mineral phase from the alpha phase to the beta phase. And then is this proposal that was developed at the Freiburg University in collaboration with Fraunhofer Institute, where instead of working in a furnace to 900 degrees, you could do it the same, not using sulfuric, but using CO2, but supercritical CO2. And then using supercritical CO2 at 200, 250 degrees, according to Fraunhofer Institute, this technology technically and economically is much better than the other option. And then it was to process this material and then to follow in the typical stages to just produce lithium carbonate by precipitation with sodium carbonate to produce a material with the quality to be used for batteries. Although in the project there are some companies, as it was the case of, for example, I remember Omnia, that was trying to use lithium carbonate from some application because it's having a biocide use. But for me, it's quite difficult to understand that the pressure of the the lithium for batteries is going to provide the possibility for other applications more than the production of lithium. And then the last case is that the one developed in Poland. Poland is having a large inventory of facilities where they were producing lead. And then all this lead, they have some alloys that are having lead all together with typically cobalt and copper. And then it's called the CONI process because it's expected to recover cobalt and nickel. And this is a very, very straightforward process where is leaching of cobalt and nickel. There are samples that are very, very rich in arsenic. Arsenic will be removed to produce scodolite. But for example, in the last list of 2023, arsenic is now considered at the European level as a critical and strategic. And then there are all companies all over the world just trying to stabilize arsenic as a waste. And according to Europe, this material should be recovered because now it's considered critical and strategic. And I think that that's all. I mean, we are starting. We should be finalizing the design of all these processes. Let's say next year, September as a maximum. They have started all the digital tools, engineering, process model, and optimization for the construction and the startup of the operation of the different pilot that will be led by Edener. This stage is led by Edener. This is led by UPC, and the other are all these typical requirements of sustainability analysis, the social participation of stakeholder engagement, communication, and other process. And that's all from my side. Maria Gonzalez, that's the coordinator of the project, she was not able to attend, and I hope I did as good as she will do it. Okay, thanks a lot.
Thank you very much, José Luis, for your interesting presentation. We wish you good luck for the implementation of the Metallico project. If you have any question for the speakers of the European project, you can make it at the end of the workshop. Now we move on the round tables. The first one will deal with the recovery of metals and minerals as an economic lever for desalination plants. The expert speakers at the round table are Guillermo Riol, Gilberto Rial, sorry, Research and Development Leader at DuPont, Nayar Hernandez, Research and Development Project Manager at FSCC Aqualia, Christopher Fellows, Senior Water Expert who made the above presentation, interesting presentation, and Christopher Chirisiadis, I think I spelled well, Brine Innovation Manager at Neon Portfolio. So, and finally, please, the roundtable will be moderated by Nicolas Nelson, C4Value Project Partner and Director and Innovation of Innovation and Technical Marketing Water at Omnia. So you can go ahead for the roundtable.
Sorry. No.
You will have to move.
Oops. So first of all, I think we're very blessed today to have some of the most intelligent brain trusts when it comes to brine mining today sitting on this panel. And I'd like to start maybe by introducing them and their roles. Guillaume, you have the microphone in your hand, so you work leading the R&D from DuPont. Maybe give us a bit of a flavor about the sort of requests that are coming to DuPont for brine mining topics. Maybe also giving an idea of which metals and minerals may be of interest from a customer perspective.
Thank you, Nick. So I'll provide just a brief introduction. I'm Guillaume Gilberto Riol from DuPont. I'm leading the Global Water Technology Center that we have in Tarragona. So if you've never visited it, come to visit us. I'm answering your question, Nick. That's a good one. What we do on the brine recovery. So for DuPont, this is a strategic line, right? We have kind of three big lines for brine recovery, and I will just try to simplify as best as I can. So the first one is obviously what we've been talking today, separating brine and obtaining valuable materials from seawater. That's one line. The other line that we have is what we call direct lithium recovery. Basically, this is treating brine lakes like the ones that are in South America. And the third line that we have, we call it minimum liquid discharge or zero liquid discharge, MLD or ZLD, known by its acronyms. And these are more kind of industrial processes. I saw in one slide that was this site in India, for example, right? That we recovered salts from industrial brines, right? And for that, we use the word fertilized brine. So talking about the specific requests we get, for example, for seawater brine recovery, we get typically the request to separate divalents from monovalents. This means extracting magnesium mainly, and we've talked today how important magnesium economy is. And for that, we use what we call seawater BR100 and 150. This is an nanofiltration selective membrane that enables to extract these divalents from these monovalents, so we can valorize magnesium, and from the other side, monovalents such as sodium chloride. And then the second material that's very important and customers are requesting is how we can purify and concentrate further the sodium and chloride monovalents. And for that, we have the seawater BR200 that basically, and also the ultra high pressure RO, right? There's these two technologies. And if you think of a seawater brine, typically it's at 8% salinity, and our customers wants to concentrate up to 12% salinity. And to do that, either you can work with a low pressure membrane, and low pressure I mean below 80 bars, that extracts water from it and gives a permeate that it has high conductivity, or you can use ultra high pressure RO that to achieve the same concentration and concentrate this sodium chloride to this from this 8 to 12%, but you need to operate at higher pressure. So we have these two options.
So thank you, Guillaume. If you mind passing the microphone on to Naira. Naira, you're representing FCC Aqualia, who are owner and operator of desalination plants. And you're also a valuable member of C4Value, yeah, and some other European projects focusing on the extraction of metals and minerals from brine. Can you give us a few words about the interest that FCC Aqualia sees in brine mining, and particularly which maybe metals, minerals are of interest, and how you see that as being an important part of the future for FCC Aqualia?
Thank you, Nicolas, for the presentation, and good morning again. So yes, in Aqualia, we are working in different projects related to brine mining. Our main objective, as we are not developers, we are operators and integrators. So our main objective is to identify technologies whose implementation in seawater desalination plants is feasible. So for example, we are exploring technologies that can produce product that we can use in our seawater desalination plant itself. For example, from brine, we can obtain carbonates and hydroxides of calcium and magnesium that can be used in the remineralization process of a seawater desalination plant, and also in brackish water desalination plant. Also, we are exploring electrochemical technologies for the production of bases and acids, and also sodium hypochlorite that can be used in our water treatment plants, not only in seawater desalination plant, but also in wastewater treatment plants. And as we are a water company, it's not only there's not only an opportunity in mineral and metal recovery, but also in increasing the water production by means of the mineral recovery. So we can increase the water recovery with different steps. So in this case, we can increase the efficiency of our desalination plants and build desalination plant compactor. These are one of our main objectives in studying the brine mining.
Fantastic, thank you, Naira. Chris, yeah, look, I know you had a fantastic presentation before, and that was a great insight into the work that you've been doing with SWCC. But at the end of the presentation, you gave an overview of a schematic that you're looking at Jabal, I believe, yeah, for brine mining. Can you just say maybe a few words on the interest and driver for that project from an SWCC perspective?
Okay, yeah, certainly. Thank you, Nicholas. I'd like to start just with a plug for Guillaume's center. So I did take up his invitation yesterday, and I can say it's well worth the visit. You should all do that if you can. So the driver for the Saline Water Conversion Corporation is essentially to make the cost of water as low as possible for our consumers, and we see adding value to brine as a key way to do that. We're very confident in our brine disposal technologies and that we're meeting the regulations and are monitoring carefully to make sure there aren't any negative impacts on the environment. So it's not primarily environmentally driven. So it's primarily driven to add value. We're in a very fortunate position in Al Jubail. So it's next to a place that's called Jubail Industrial City, which is a huge area of industrial development. So we're about halfway along the Saudi Arabian part of the Arabian Gulf Coast, so midway between Kuwait and Bahrain. And there are industries there, a very large chlor-alkali industry. Their sources are currently surface mining. So there's what's called sabka, which are these shallow salt deposits. They realize that development of those is not sustainable in the long term, and we felt that we could meet their need for salt. So that demand is growing, and as we saw, that's the main economic constituent in seawater at the moment. Also, the need for bromine in the kingdom is growing. Currently, 100% is imported from Jordan, which is, I mean, we saw such a great amount of supply chain disruption recently. I think every country is swinging back and thinking, oh, what can we do on our own resources? So the bromine is a very important part of the economics of that. And yeah, very, very briefly, you didn't see it probably because I went back too quickly, but there's magnesium hydroxide is a byproduct of the process at the moment. So by itself, it's not economic at all, but there's a polishing stage of the monovalent brine to get the magnesium down to the right level for the chlor-alkali industry. So this generates magnesium hydroxide as a byproduct. And we're currently looking at the potential of using that in remineralization within our system. So hopefully I've answered the question. Those are the main sort of economic drivers for SWCC.
That's perfect. Thank you. And finally, Christos, I think you're leading most of the discussions from Worley's perspective with regards to brine mining. Can you maybe say a few words about the requests that are coming into Worley's for such projects, and maybe a few of the metals and minerals that are of customer interest?
Yeah, gladly. Thank you. So my name is Chris Corsiadis. I am the Brine Innovation Manager in Worley, and my main focus is on the NEOM project. Is there anybody here that doesn't know what NEOM is about? Can you raise your hands? Okay, so quite a lot of people. So NEOM is the city of the future that is currently being built in the Tabuk area in the Saudis. Yeah. So they have essentially to build another Dubai in the middle of a desert, and this means that they need a lot of water. We're talking about a desalination plant ranging from 500 MLD, 500,000 cubic meters per day, that we need to build now, all the way up to 2 million cubic meters per day. And this means, as you might well understand, a lot of brine. Yeah. So we need somehow to bring down the operational costs of this desalination operation by producing viable salts and minerals. Yeah. Okay. So apart from the NEOM project, which is probably, if not the biggest mega project, one of the biggest ones currently worldwide, there are a lot of other similar cases worldwide, ranging from lithium to brines from neutralization of toxic wastes. And it is always there are always very specific drivers of either water reuse or a very specific salt that the end client needs. Yeah. But here's the deal. You need to understand that with brine mining or brine refinement, yeah, you see, I was paying attention. So we can create multiple revenue streams. We are not we're not in a tight space to produce only for example, sodium chloride. Yeah, but from my side, I have seen definitely an interest in magnesium. There is also an interest in fertilizers. Lithium in the lithium rich areas. I don't think the presenters here left something out that I can talk about. But the point is not what the minerals are, but how to get there efficiently. Anybody can do GLD. Yeah, doesn't mean that they can do it efficiently, and there is a viable business case. You need to find a way, and this is what we spent our time and sweat on for the last years in NEOM, to find the best configuration and the fine-tuning it needs to have the lowest OPEX possible, because OPEX, the operational expenses, is what will make or break your project. Nicholas?
Super. No, that was fantastic. I mean, maybe while we're just on the topic of drivers still, we had talking about captive use of products that are produced by a desalination plant owner. We had supply chain, concerns for access to critical raw materials. We had driving down the cost of desalination in general. Yeah. Is there any other drivers that you felt from the market for wanting to go down this route of extracting metals and minerals from brines?
ESG.
ESG,
Yeah,
yep.
That's something to definitely to. So the ESG checks will become more and more popular as the years go. The decarbonization needs, yeah. So the carbon tax in EU will only go higher and higher. I don't know.
Yeah, thanks, Christos. And I just wanted to build upon this point of sustainability. So for us, this is a strategic place to be and to invest, right? So if you think about that, we are in an environmental crisis, and there's a nexus between water, energy, and critical or strategic raw materials. And in my opinion, brine recovery is really intended to address all these key concerns, right? So from one side, we produce water. This is clear. There's droughts. We are living it now. Just in the region of Catalonia, the dams are at 18%. So we are about to enter into a crisis. But I would say that is worldwide. So from one side, we have the water nexus. Then we have the critical raw materials. We need to source them in an environmental friendly ways, right? We don't want to destroy mountains, right? And we have the perfect case here of reducing this discharge. And then we can also integrate it with the decarbonization, right? By integrating green energies like solar energies, for example, extracting carbon from the air and using this carbon to go deeper in the value chain of producing organic and inorganic chemicals.
Thank you, Guillaume. I think when we looked at your presentation, Chris, we saw that in most cases, the cost to extract a lot of these metals and minerals are not more efficient than current practices, more on a linear perspective. Yeah. What role does regulation play to help drive the economic argument more towards circularity and make this more economically viable?
Yeah, this really ties into how I was going to answer your last question. I think was that there's still a level of uncertainty as to how much of a premium the market will bear for a greener product. So the regulation is really, I think, still the primary driver there. If there's a push to say no, you can't do this. You need to use this more sustainable process, even if the cost is higher. So I think that's still very significant and likely to become more so.
Very good. Guillaume, you're working on lots of new developments. Yeah. What do you see as critical to close that economic gap from a technology perspective to make the extraction of metals and minerals from seawater brines or other brines in general more economically feasible?
So, the brine recovery, it's a very interesting technology, right, to reduce the total cost of water. We've been discussing here the economics by your talk. And this is very interesting because when we concentrate the brine up to 12%, we can get much of the value. But if we can concentrate it further down to 22%, we were before discussing it, Christos, how new technologies can help achieving that. That could be the osmotically assisted reverse osmosis or the low salinity salt rejecting reverse osmosis that can really close this gap, right, and concentrate the sodium chloride from 12% to 22%, so that we can replace thermal processes such as an evaporator and go down to this 22% concentration to make it even being able to extract more value out of the minerals that we concentrate. So this low salt rejecting reverse osmosis is a technology that we'll see developing and that will really help closing this economical gap and making it more attractive from an economical point of view.
Super. Naira, in terms of business models, is there an interest for FCC Aqualia to look at the extraction of these metals and minerals by yourselves, or engage third parties to bring technologies onto the desalination plant, or how do you see that playing out for a future installation where you're taking metals and minerals out of seawater brines?
Yeah, we are contemplating both options. As an early adopter, to use the product that we can use in our desalination plant has a faster implementation for us, and this is a real need in our plants. But also we contemplate the possibility to produce other metals like magnesium or let's see, magnesium, and in an industrial level of volume. And in this case, we have to work together with the companies and end user, because they are who have all the knowledge about the market, the network, the transportation. So we are contemplating both strategies for the market.
Okay, thank you. Maybe just a general question to all of you, no one in particular. So seawater is 85% sodium chloride. You know, how important is that we generate business models that we can valorize that sodium chloride to get to the other, let's say, lower concentrations of critical raw materials?
I'll let you have a go first.
Okay, so yeah. Nicholas has a point. Yeah, we need to find business cases for sodium chloride if we are to make brine mining a success. And we have a couple of options right now. We have the simple table salt. We have chloralkali. Yeah, pretty big need there. And we have also the pharma. But or perhaps the energy storage as well, fourth option. We need to diversify and find strong business cases. Sodium chloride, for better or for worse, is, as you mentioned, the biggest contained salts in any industrial brine. Yeah. And we need to put our minds together and figure out how on earth are we to better take advantage of it. And I think DTRI had an excellent idea with the chloralkali plant that is nearby. Yeah, just concentrate and just feed with a pipe to the electrolyzers. Yeah, so we need to be a bit more creative with everything, case by case, trying to find the best configuration in order to serve the best our business case.
Thank you. Yes, as I said, I think this is really the rate determining step for a lot of these things. So finding the market for salt and thinking outside the box. There was 2,000 years ago reports of a city built out of salt on the Arabian Gulf, and I think there are people working on using salt as a building material. So although this might not need a very high price, it might also not need a very high quality. So I think that's one potential, thinking a little bit outside the box, that in the future might be wanting huge quantities of salt and making a lot of these other things possible. Sorry? No, with chlorides, sodium chloride.
The project we've been working on, C for Value, is focusing mainly on the critical raw materials, right? So we're talking, gallium, scandium, vanadium. But most of the business cases we've been looking at is more of the common sort of materials that we're using, sodium chloride, magnesium, bromine, yeah? Is there opportunities to valorize then these other critical materials once we've built business cases for the more prevalent ions and outlets for those?
So particularly, I think that there's a case for addressing this need of critical and strategic raw materials. Especially, we've seen interest on the rubidium for defense applications, and also because of its properties as an energy carrier, and also in uranium, right? So seawater has an interesting concentration of uranium that can be recovered, right? And with that, we can also secure other energy sources.
Thank you.
I also like what you said yesterday, Chris, by the way, on how the sodium chloride can be used from the brine instead of just mining it from Jubail.
Thank you. I think, I mean, so we've been talking about desalination, but the title of the day's whole presentation hasn't been, desalination. It's other critical sources. And one thing that's become more and more clear to me, living in Saudi Arabia, is the problem of produced water from oil and gas. So this is a huge volume of water. It's getting larger, and there's a strong pressure for zero liquid discharge there, where there isn't necessarily with desalination. This is being generated in inland places, and disposal is a big problem. And the glass half full side is that these brines are often very, very much richer in these critical components. So I've often tried to damp enthusiasm about lithium from desalination brine, but I believe there are oil field produced waters out there where lithium, for example, is viable. So if we just lift our vision a little bit further than from the sea, I think that there's a lot of those critical raw materials there in other brines.
And that feeds a little bit more into what you were saying earlier, Guillaume, in terms of the request coming from DuPont may not be for lithium extraction from desalination, but from other lithium-rich brines.
We have, for example, a line that we just launched this year. It's called line XD, reverse osmosis membranes. And this is a membrane that has two main features. One is that it can really separate the lithium from any divalent, like magnesium, so that it can be extracted properly from these lithium lakes that there's in South America, lithium-rich brines. And then it's also very, very durable. So it can last twice as typically what other membranes could last. So for us, that's a line that we already have. We launched it this year, and we are just getting projects on this application. And this is an example of a strategic material.
Sorry, Nicholas, if I might divert a little bit from the conversation. I would like to repeat to you all something that I was trying to convey in Aquatech. This technology space that we work in, zero liquid discharge, brine mining, it needs success stories in order to grow. We need to find real, viable business cases, go after them, and make sure that they succeed. Unless we do that, we will forever be staying in this small room talking about the possibilities of the future. We need to collaborate, disseminate information to each other in order to create a better understanding of the technologies and the business cases that we can create. And if we don't do it soon, then we will spend the next 10 years just, saying, oh, it would be great if the system would look something like that.
That's the interesting, sorry.
Oh, just, I was wondering, Naya, do you have an idea for the timetable within Aqualia for, is there like a vision for when they want to swap over to using these internally sourced chemicals in their desalination processes?
About the products do you see in, well, we are exploring and we are analyzing the viability, energy consumption, also exploring the value in the market, but because it depends, maybe is viable in Europe or is viable in Saudi Arabia, but not in Europe. So we have to study case by case because it's a complex situation, and we have to analyze each scenario.
And have you found, Naira, that you need a complex business model in terms of you need outlets for all of or a couple of the metals or minerals that are in the seawater brine? Or is there enough scope for just a singular metal or mineral to build that business case and then build on top of that?
We are analyzing individually, but for sure, if for a process to be viable, at the end we have to recover more than one. Yeah.
Sorry. It says so. Here's another idea about how to deal with brine mining. And so instead of trying to deal case by case, yeah, how about we create a limited amount of separation centers? Yeah. So for example, fractional crystallization. And we create a lot of mixed salt operations all over Europe that ship their products to these said locations. So perhaps it makes more sense in the end, commercially, especially in Europe, since we are like a small area, to have like 3-4 places that we can separate the salts and thus you have the necessary quantities to make a good business case. And this is, for example, what NEOM or SWCC do. We have like a huge amounts of brine to deal with, and thus the necessary the volume of products to make financial sense. Yeah, but here in Europe we don't have this amounts. Yeah, to produce viable commercial products.
Yeah, but I was sorry. I was thinking with you're saying that we need to get wins on the board, as we would say in Australia. That the sort of thing Aqualia is doing, where you're looking at producing chemicals for your internal use when you've got such a large internal consumption. That might be a way, you know, where a company could show leadership. You know, maybe taking a little bit of a hidden loss, but showing that it can be done. That was my point.
So yeah, Christo, so that's an excellent idea. What you mentioned, we really need to focus into creating case studies, right? To show that what we're talking is not our imagination; it's the reality, right? And we are now in the future. And just wanted to comment as an example also on another application that it's not these lithium brines or seawater, but more MLD and textile industries. We wrote a case study 1 year ago about a case in India. They had an operating cost of $1.5 per cubic meter. And thanks to being able to valorize the sodium chloride, the whole operating cost could be reduced just to 50 cents per cubic meter of water. So customer was extremely satisfied because at some point, and I think you mentioned when we met in Tarragona, Christos, that producing water is not the benefit. What really drives the main investment and revenue is the minerals that you can extract. And this is happening right now.
Start seeing the water as a byproduct, not the main goal here. But Chris, correct me if I am wrong, right? In the end, what drives the market are the regulations. Yeah. And most of the times what we do is wait for to react on the regulations. And how do the regulations take place? Someone pushes the politicians to take action. And as usual, most of the politicians will take action when we are up to here with the problem, right? The same happens with water. Right now, water is very, very cheap. And this is why nobody pays attention to it. if we try to educate the people and raise awareness of the real problem of water resources right now, that we don't have that much water as we think we do, then someone will push the politicians to go in the parliaments and vote for water reuse. We need to push the people, the broader public, to understand that we live in an area in an era of limited resources. Once we do that, then we will have someone who will vote for better application of water resources. And I don't know how to do. I don't know how to convey that more clear. That if we don't take action as water professionals, then the opportunity will just fly away.
Thank you, Christos. I think you can see there's a lot of and know-how on this stage, fortunately. And I hope that's given a bit of insights to the different connections that our guests have in this topic. We now have the opportunity to open up to the floor. If there's any burning questions that haven't been answered so far, please raise your hand and we'll bring a microphone round. We also have the opportunity for anyone who's connected online to write into the chat a question, and we will hopefully have some time to bring it to the floor as well.
Okay, thanks. I have two comments. One is to Nayara and the other is to Guillem. I totally agree with Christos. Everything I'm working, you need to start with the project that is the easy one to be finalized and to have success. And the success cases is I 100% agreed on that. No, it's a short comment. I remember I realized for a large desalination plant, the amount of chemicals that you need and you could produce from the brines you produce is less than one. You will be using less than 1% of the brines that you in a large. For those calculations we did for the El Prat seawater desalination amount, you are not using too much sodium hydroxide or hydrochloric acid for cleaner and so on, and maybe you will use 1% of the sodium, the minerals that are in the brine. And then I think always any project should be linked to an industrial case study where the minerals you are set to have the success that Christos is requesting. And the second one is to Guillem. Is a favorite case that I explain to my students. No, there are two large programs on uranium recovery from seawater. In Japan, in the 80s, they spent millions of yens, and they build everything, but they are not producing uranium from seawater because Japan is having the problem is having nuclear power station and they don't have mines. Okay, but after that I was totally shocked. In the last 10 years, USA spent thousands of millions of dollars to make the same, and at the end they just finish the project, because the problem is the sorbents that you need, they have a capacity of 1 milligram per gram. Is 1 gram per kilogram. 1 kilogram, 1 ton. I mean, to recover 1 kilogram of uranium, you need 1 ton of sorbent. I mean, it's not. I don't know if it's thermodynamical problems or it's not reliable, I think, or economically feasible. Just thinking on removing elements from brines that are in the parts per billion level is what the idea that I have.
Thank you for that comment. I think there's a lot that we can learn already from past case studies, whether it be already magnesium hydroxide or bromine, as Chris mentioned, from seawater brines.
Yeah, my name is Fidel Grandia from Amsterdam. I'm exploration geologist, so I'm from the dark side of the force. So I'm not an expert, and I'm really impressed of your work. But comparing primary mining with all of this, primary mining has an advantage that with very, very few centers of production, we have huge amount of metals. And this helps keeping in mind that in our world right now, we have very few countries processing metals, right? So in terms of distribution, helps having just a bunch of production centers, and mining companies do that. Basically, they have not many production depending on the cost and the price. And my question here is, if eventually all these technologies you are developing work in the future or in the coming years, maybe I'm wrong, but I imagine that we'll have multiple production centers. Is this an obstacle to reach the market? Because we have a lot of places producing scandium or any metal from the brine, but we need to send it out to a processing place. So is this an obstacle for the market?
So first of all, let's take the case of conventional resources mining. Yeah, the way I understand it is that it is also not simple or cheap, and the extraction costs have only gone up with the years, with the rise of electricity costs and environmental regulations. Yeah. Plus, you have mining the ground is a finite resource. And from our side, when we come from the brine mining concentration and separation, we see that one or multiple locations, yeah, provide even better options for the end customers because it means no shipping costs. Yeah. So if you are, for example, if you have a case where you need a lot of salt coming in with trucks from the other side of the country, yeah, that doesn't make any sense. If you can get it next door from the sea or from an industrial wastewater source. So I see only benefits from one, brine mining, two, from multiple production centers, if this answers your question. Guillaume?
Well, I'm not defending primary mining. The point is that, well, I'm more expert in other metals like rare earth, and we know that if we want to produce something, we need to ship it to China, basically. So my question was basically if instead of sending not large amounts of metals from everywhere is not recommendable compared to sending much from one side.
You have also geopolitical. You have also the geopolitical and strategic like points to take care of. Yeah, and the pandemic and the Russian war proved that how much it is needed for you to get your stuff from your backyard.
That's exactly what I wanted to comment also, so that geopolitically, it has a lot of relevance, especially for the European Union, to be able to source your own critical raw materials and not be depending on other countries that maybe they are more unstable, at least they are not in your control, right? And we have sea, right? The sea is just here, right? So we can just source these minerals as much as we can. And personally, I also think that the fact that we can integrate the whole process helps also into improving it economically, right? It's not that we just need a salt mine, a magnesium mine, right? We have everything integrated and we can source just the materials and plan our production, like what we do in seawater, right? Why we build wastewater reuse plants and desal plants? Because we want to be independent of whether it rains or not, right? If we build a desal plant, we know we'll have 100 MLD capacity every year, right? And for me, that's the same. And personally, something also that I like about brine recovery is the EH&S aspect. You mentioned, Christos, that pit mines are not infinite, right? They are finite, but also they pose a EH&S risk, right? Workers can suffer injuries. Brine recovery does not have the same kind of risk. And going to your question, Jose Luis, thank you for asking. So personally, the inquiries, I agree with you. It's in very low kind of concentrations uranium, but the fact that we are getting attraction from customers tells us that probably it's also linked to this geopolitical independence, right? Most of uranium mines are in Africa, other countries, Russia, that they are probably, at least not locally, right? And so I see both things pretty much well interlinked.
Thank you, Guillaume. Look, and maybe just to wrap things up, because we need to move on. I think we know that, you know, linear economies is always cheaper than circular economies, yeah. And this is why when we go back to say we need regulations to force the conversation towards more circular solutions. And it's really, I'm really happy that we're working on topics of circularity now, that we're going to be prepared for the solution. It's too late to wait for the economic iceberg to tip. We need help from the European Parliament, and it's really happy to see that they're also implementing, you know, working bodies on critical raw materials and circular solutions, forcing the conversation in this direction. So I think thank you all of our guests. Unfortunately, running out of time for any more questions. I'd suggest if anyone wrote any questions online, then we can pose these to the guests later on, and maybe they can respond. Yeah, and with that, I'll pass back over to Aina.
Thank you very much for all the speakers for this interesting discussion. We will now move on the second round table. Thank you very much again. So we will move on the second round table, and we approach the end of the workshop. The discussion of the second round table is critical raw materials market, barriers and opportunities. And we have with us José Luis Cortina, chemical engineering professor who has previously presented the Betalic project, Fidel Grandia, project director at the Waste Management Department at ANFOS 21, Philip Bartelmes, Vice President for Process Design and Innovation at Omnia, and we have Frederic Clarence, Director at the Waste, Energy and Environmental Impact Technology Unit at the Sustainability Area at Eurecat, who will moderate this roundtable, focused on discussion the critical raw materials market, specifically for unconventional sources. So the chair is yours.
So thanks to all here and also on the online audience. I think the last two questions was just introducing this table. Here we talk about critical raw materials, I think connected and not connected to the brine desalination. I think we can be quite open, but I think Chris in this nice introduction talk about mainly the major elements. Also, Christos mentioned that we need to see the market on 10 years. So now we are just focusing on these small elements critical for the economic value, for the economic relevance, but we need to talk about the market. So there are elements, normally trace elements, critical for the economy, but how is this market? How do you think that is connected the real market? If we can supply probably tons of scandium, we talked with Fidel in the coffee break, probably there is no who can consume here. So what do you think that is the real market, or how this can be coped, this market, on this 10, 15 years average, the evolution, the need of these plants and the market? What do you think that is the real situation of the current situation? No, maybe Philip.
So good morning, everybody. I'm working for Omnia 6 years already. I'm representing more the business, not so much the R&D part. So I think it's a good question to be addressed from my side. We all see the mega trends we're heading to, electrification of the society, food. So I think it is pretty clear who will be the customers. It's more a problem of accessibility at the right cost. And I think all these projects, they are around the topic how we tackle this as Europeans. I think there are areas, regions in this world, they are a little bit more lucky in having access to these raw materials. And we see that they take more and more power in getting their products into our market. So really the challenge is how can we assure the access to these raw materials at the right cost? And all these projects are actually helping not only to extract critical raw materials from brines of seawater, but all the technology which is developed during these projects, they will help to recover raw materials from industrial brines, from all sort of brines. You talked about the oil and gas industry. I've been working there for 10 years. I think this is really the interesting part of it, that we as Europeans, we are creating new technology which will help us to access these raw materials in the future. Also related to future recycling processes, which will help our circularity approach, and the technology that will help.
Okay, thanks, Philip. I think related, you mentioned two of the, you say that the countries that have other potential resources of this material are lucky, but here we are talking about those unconventional resources probably to supply at European level. So also I think we need to perform, also in the previous table is mentioned, we need to perform sustainable processes, and also in some terms talking about the market, the price, probably is expected that from secondary materials, the products should be also cheaper or cost. How do you think that we can handle to overcome this truth or this myth of this, that recycling or byproducts could be cheaper and more sustainable? This is a true statement. Probably it's just not full true. What do you think about this aspect? What these type of projects can help to really overpass these barriers or this myth that pass that as you will be from secondary sources, we will have a more sustainable and more cheaper source. This is true. What do you think about?
I will explain, let's say, my short experience, because in the last 4 to 5 years, Frederick knows, we are participating in these EIT projects where you are working on upscaling, and at the end you promise you will develop a process, you will develop some materials you need to put in the market. And then after you need to return back all the money that the EIT raw materials just provide you for financing the project. And then we are doing a very, very large effort in this stage. And I will say that there are two things. The first one, you are developing your project, and then you have the need to technically achieve, for example, the one of the antimony and bismuth recovery project. You need to recover antimony and bismuth with the highest purity, and then trying to optimize the properties and so on, and then try to minimize or to reduce the cost of the chemicals that you are using. But at the end, you get some materials, and then the next stage is you need to provide who is the company that is going to buy that. Typically, in a secondary, in a project recovery, some elements from some secondaries or some waste materials, you are not going to be able to produce the expected quality that you need, and then you are in the hands of companies that are developing this last stage. Okay, our experience is quite difficult for this case to reach a material that could be put in the market, and then you are requesting to find one company that is able to, because maybe you are reaching 98% or 97% or 99% purity in the element you want to recover, but then it's 0.1, 0.5% of arsenic, and then no one is going to buy that because it should be less than 0.1, and then you are in the hands of a second stage of this change, just to purify or to produce a product that is in the market. Then one thing that we face is typically companies, when you are providing a material that is starting from a waste, they are not buying the waste. They are just purifying for you. They are going to charge the cost of this purification stage, and then they are returning you the product. Maybe they are able to put in the market. And then my experience, Frederick, is, or our experience is, we are not going to get a material that the product is going to be much cheaper than the one that is produced. I mean, I think that a realistic objective is to get a product that the value in the market or is going to be competitive. But I will not say that it's a state that is much cheaper.
Okay, so will be difficult. So this statement that normally is tried to be on the traders is not true from your side. Fidel, I think your company is between probably universities and producers. I think it can help. So what do you think projects that with low TRL like C4 value and some other projects that are showed this morning can really help the industry? How can be implemented in the industry? How we can work in some way to shorten times to the scale up or to get to the market from your experience or your role from your company?
Yeah, well, my experience is basically on rare earth recovery from secondary mining, and this is a quite paradigmatic example because probably you know the case of the rare earth production in the U.S., the Mountain Pass. So we are really shocked what happened. I mean, the U.S. decided to restart the production, to resume the production of rare earth. But after that, they succeeded in producing rare earth for competing with China. And after that, they realized that they need to sell rare earth to China for processing. So in case of secondary mining, we face a similar problem. So first, the cost of the rare earth for final or for processor, the companies that process and go up to the value chain, it's for them is much cheaper to buy raw materials to country that don't include the environmental cost in the price, right? So if Europe intends, well, first, Europe has a lot of primary raw materials, a lot, but we don't want to mine them. It's a good option because environmentally, mining, I think it's treated in a fair way right now because the mining activities are more sustainable now, but it's okay. Let's play with the green option. So we don't want to extract more raw materials from the primary sources. Let's have a look at the secondary sources. But of course, we cannot compete if we don't include the environmental cost, right? So the first question when you try to put your product in the market is how much is your product? So if the first definitely the first problem is that Europe doesn't have the next step of the value chain. If we process, or in general,
The small companies.
yeah, but in case of lithium is not produced in China, but 80% of the lithium is processed in China. Cobalt is even worse. Almost all cobalt is produced in Katanga region in Congo, Democratic Republic of Congo, but all of it is processed in China. So I think before discussing if we can produce something in Europe, we need to talk about, can we process it after that? So this is for me, it's the question, the key question. Then we can talk about the part of the price, the environmental issues, but it doesn't make sense if we produce something very well, sustainability and so on, and then we send it to China.
So Philip, I think Jose Luis, Fidel agrees on the same issue, on the processing, on the purification of steps, on real introducing into the market. As you, one of leading companies on the market, what do you think about these feelings that probably can be shared by most of us, that we really need to improve all the capacities of production of manufacturing in Europe, because it's not just to keeping the value of the products, it's not keeping the industry as a set, probably. What do you think about this? Because I think Jose Luis and Fidel in different words agree that the processing, the incorporation into the market, because at the end is the market, the opportunities that can bring these new steps on the critical raw materials probably arise to enhance the recovery on the European industry. What is your thought?
No, I think we have identified in Europe that we need to process also these materials in Europe. I think there are multiple battery factories right now under construction, which need a huge amount of anode and cathode material. We have a competitor, as OMIA, we have a competitor who is already into lithium, who is into synthetic graphite. So I see actually that we are ramping up, right? These new economies, they are all about velocity. And we tend to be a little bit slower than other countries in this world. This is due to we want to be more sustainable, which is a good thing, but it takes out some velocity. I think we have been slowing down in educating our generation. If you compare this with China, to take one example, the education in this country is amazing. And we see this with the ramping up of filed patents in China. I still believe that we have in Europe an incredible potential for investigation and doing something different, which will increase our competitivity further. So I think, yes, we have the need of these raw materials to process them here. Also, a big market is here. It's not the whole market, but Europe is still one of the biggest markets in the world. So I'm pretty optimistic. I mean, we as OMIA, we are not into metal minerals. We are into non-metal minerals like calcium carbonate and dolomite and gypsum, but they are also used in many markets which are mega trends, food, construction, electrification. But we see that the technology which is developed for the critical raw materials help also us to actually produce non-metallic minerals in a more sustainable way and to increase our ratio of circularity. Right, we are pretty linear right now, but with these new technologies, we are able to get more circular.
Yes, if I could say, I think there is a good history that could be shown as a potential model. We are not having in Europe phosphatic rock, and we are importing all. And then phosphorus is considered critical element in the European Union. And I remember that the first countries that were developing the technology to recover phosphorus from secondary resources was the Netherlands and Germany, just getting from the fly ash, from the mono incineration facilities for the urban sewage sludge. And I remember it was a meeting, maybe it was 2018-19, when you try to, it's possible to recover phosphoric acid from fly ashes with the quality to be put in the market? Yes. What is the price of the phosphoric acid compared with the one produced is much higher. But I think Germany was promoting that this difference was going to cover by the government. I mean, the only way, I mean, I think that I'm supporting that raw materials that are going to be produced from secondary sources, in most of the cases, are not going to be much cheaper, and we are lucky, are going to be close to the values on the ones that are produced in a traditional way. Then always the European Union is having the possibility for those that are considered criticals is just to have some regulatory help, just to make possible these successful projects.
Just let me add, do you know why the traditional phosphate industry is cheaper than conventional sources? Because they don't include the environmental cost of the waste. So right now we have million and million tons of phosphogypsum, fluoride sludge, and it's not right now reusable or included in the valorization process, and we are working on it because of the radioactivity. Okay? So if you include the cost of recycling and managing the waste, probably it's not that cheaper than the unconventional sources. So my point is that sometimes we are looking for new things, new inventions, and the reality is that we don't have time. We are running out of time, because in 10 years, someone from the EC and from the US said all cars sold in the region will be electrical. And I don't know we can meet this requirement, but this is the reality. And I think, especially for research, we need to look for synergies and something that can help traditional industries to produce these raw materials. And the phosphate industry is a clear example. Phosphate industry uses a raw material which is phosphorite, which is, for me, the less interesting is a phosphate, because it has a lot of things, especially rare earth. But for example, uranium, if you want uranium, don't look at the seawater. Look in this waste. We have 400 ppm of uranium. So instead, not instead, sorry, but if we want to, this is why I like this C4 value project, because we have an activity already in operation, which is desalination, with a market which is growing up a lot, especially here because we don't have water. And it's the same for the phosphate or phosphoric acid industry. This is going to be necessary in the future for the fertilizer production. So let's take this advantage of a industry which is growing with well-known technology. Let's develop research to take raw materials from this kind of industries. Okay, instead of looking at rare earth somewhere else, let's see how we can clean the waste from the phosphate industry, clean from thorium and uranium, and recover all this. And this is the same for scandium. Aluminum industry is producing a lot of scandium in the red mats, but the red mats are there, just sunbathing, right? So my point is that the research right now, taking into account that we have 10 years to go to the new world, we need to look for these unconventional sources and try to, and we have it in Europe. We have a lot of red mud basins with tons and tons and tons of scandium. And now some companies are starting to include the scandium processing in the aluminum industrial process, right? So.
Okay. Both of three now talk about sustainability. I think projects like C4 Value will, I think, introduce some kind of complexity to the processing, but can be also introduced in mining or in these red maps also. But what do you think? The critical raw materials will be real an opportunity to enhance the circularity because we are recovering more products from the same source, but also we are generating some byproducts or streams. In some of the projects, I think in the life, they try to use also the byproducts to produce the reagents to introduce. What do you think about this opportunity at project level or at a real level? Also, that this recovery or these new markets for critical raw materials can enhance the circularity or the sustainability of the industry, of the sector.
Yeah, I think it's a difficult question until we do not answer the question about the cost, right? And I'm coming back to this example of the phosphor because we are into a project right now where we help a company to let's say solve the zero liquid discharge problem, where we have these calcium chloride and magnesium chloride brines, and we as a calcium carbonate producer, we can actually take advantage of this and make a calcium carbonate, precipitated calcium carbonate very easily out of it, but at a very high cost. So you can only be successful if these side products, they have actually a property which you can't reach with a natural raw material, which we achieved. Still, we are far too high to have a business case. And I think Christoph made a very good point. You need to have a business case. And the business case can come from performing in a certain application, but also from regulations. And I think we are heading into this direction now in Europe. We have already CO2 certificates, which are paying off for a certain effort you have to do on the technology side to succeed. And I think this will increasingly improve the business case. We as OMIA, we want to invest in this in a strategic way. We would accept actually a higher cost of production to be able to increase our circularity. But definitely all the critical raw materials, phosphor being one of them, they need to come at the right cost.
My add is in the 5 years back, maybe Frederick, 10 years back, I was totally convinced that the only way to survive in our planet was to convince everything on the sustainability concept. I'm totally shocked talking with big chemical companies that at least in front of you, they are providing a message that they are going like to be the leaders of sustainability. I mean, and I remember one colleague working in Covestro said she came the CEO from Germany. I explained, look, we are producing this polymer, this MDI is going to be converted to polyurethane, and a few bags we will have the polyurethane waste, and we will start just working. The future of our company is going to be that. You know, it's more than sustainability, is the lack, or it's connected, the lack of resources, and then circularity or the lack of resources maybe is going to be, let's say, a very, very critical effort. Also, there are very concerned on the issue of they are used to have raw materials from maybe everywhere, and now for them they are taking into account the CO2 emission for transportation. Then I think it's a mixture of the sustainability and then this circularity or lack of resources and so on. But then this example that was providing, I think I like it because, but sometimes when you are working on that, these circularity issues, always you have a problem. You have one stream and nothing that could be done. And then I could say that it's a similar case. It's a mining, we are working for a mining company. It's just to separate sodium chloride for calcium chloride. Sodium chloride could be reduced, but the problem is what could be done with calcium chloride. I mean, it's a very perfect project on circularity. It's not promoted by sustainability because it's an inland project, and then it's a regulatory issue that in Europe, in the north of Europe, some of the countries, they realize that the flow rates of the rivers are decreasing and they could not continually discharging brines to the water. And then it's a regulatory concern, and then everything is perfect, but then you face a new problem. You need to provide an exit to a stream that is going to be some 100,000 of tons per year of something that you are not able to provide a business solution. Then I'm convinced that sustainability is a sustainability plus the lack of resources and circularity is maybe this binomium that is going to be helping us a little bit.
Yeah, I agree that circular economy is, I mean, I haven't seen any circular economy project. We tend to say we are promoting circular economy, and all companies talk about circular economy. And actually, what we do is valorization, right? It's I have attended a lot of conferences, and the title of the conference was the new perspective on circular economy. None of the talks was about circular economy. None. Basically, because we understand circular economy in a wrong way. We are talking about valorization. We use a brine that otherwise would be discharged to the sea to valorize the brine to take something. Okay? But this is not circular economy, it's valorization, which is wonderful. It's wonderful. And yeah, I agree with you that sometimes many companies, it's fashionable, say, oh, we are doing circular economy. No, we are doing valorization.
I like to call, as Fidel said, the names by his name. It affects or contributes to circular economy, but we are talking about valorization. I agree. I think it's a good sentence. I think here we show a lot of projects. It's research. What do you think that will be the right collaborations, consortia, agreements to really boost all this market or the opportunities of the critical raw materials? Just an European or live project to demonstrate will be enough? Will we need to create more joint ventures between companies? What do you think that can be really be the right moment to integrate all the different aspects of these developments to really boost the critical raw materials market?
I think this is a very good point. I think this is super critical that we have the right alliances in the future. We talked about urban mining today. Today, the owners of urban mining value streams are companies which are not into raw materials, actually. But so they do not have actually the knowledge how to market these products. So they definitely need people who are into product development, like Omia, like Imerys, or like these big mineral players. So I think it is super critical that the interaction between various areas of the industry is enforced.
I totally agree with Philip that owners of the brines are water that are producing now, basically are producing water. And we develop process and to produce chemicals, and then they need the right partners. And then I totally convinced that it should be, let's say, the need to have like a symbiosis or in the project or in the business model, the companies like Aqualia is going to be requested to be working with neither the companies that are producing the chemicals or whatever, because I could not see, maybe, you know, the projects in Saudi Arabia, you know, they are great, but you know, in Saudi Arabia or the NEOM projects, they have all the money that they could, maybe. And but even that, I think, for me, are very, very important to succeed, because there are going to be examples, okay? But then, you know, it's you have done that, and then but let's going to move to Spain, no? And let's find the closest desalination facility that we have. I will say that for me, it should be totally connected to one desalination plant that is connected to the industrial area, because the potential chemical partners are there. And then, you know, it's I'm just thinking that it's not going to be developed by the companies. Otherwise, it's a new type of company is created where it considers the seawater as a raw material. But then it could be totally different, that not requesting them to a desalination facility.
Yeah, I totally agree that one of the problem we have is that many companies, big industrial companies, are not aware of the raw material issue. So, and we need a kind of education and telling them they can play a role in this business. I remember meeting with a chemical company, and I told them, do you know that you have a lot of rare earth in your waste? And the guy was, and I said, and it's worth 100 million euros. Oh, sorry, you said what? What you said, rare earth? So at the end, sometimes it's about explaining things or meeting with the big companies and telling them that they can expand the businesses. the good news from Europe is that right now many of the calls, the European Commission funded calls already include TRL very high levels. I mean, it's about 6, 7, 8. This means that the budget of these projects are 7, 8, 10 million, and this means that a big company needs to implement at least a pilot plan in the project. And I think this is a good direction. We need to get companies involved in a big project. Again, I totally agree that success stories are needed, and I think this is the way: is first to find big companies, to get involved in the projects, to provide the framework in terms of budget and means. And I think is the fastest way to reach the markets. Otherwise, we have a so large gap between R&D and markets that cannot be filled right now.
Okay, thanks. Just one last question before opening the questions to the floor and the online. I think in some parts we say that we have not the market or the processing that will be more expensive, more complex. Sustainability, it's true, but will generate other byproducts. But just from the customer perspective, will be the benefits. You say, Philip, that Omnia is able to take more cost processes that will be more sustainable. This clear will be one statement, but just in one line, because we are short on time, what do you think from customers' perspective that will be the benefits of these new sources or unconventional sources for critical raw materials?
I think clearly the availability of these raw materials, because we have political circumstances which are limiting the availability of certain raw materials. I mean, if you would have limited access to cobalt tomorrow, we would have a serious problem with high level battery technology, which we have today. So you see, the availability is really the critical thing, and we need to do everything in our power to keep being able to access these materials.
I'm not a customer, but I will add some information that was provided from Omnia, from Barcelona, that for them always reclaiming is traceability, because they, according, I don't know if it's true in Omnia, but you want to know in which way those material was processed. And sometimes if you could not get, today you buy lithium carbonate, you could not have information in which way it was done. And then, for example, according as a customer, according to Omnia, traceability was a very, very important parameter for them.
Yeah, definitely. I wanted to point out this aspect. If we need to, at least Europe decides to go for the green way, also we need to take into account the traceability of the sources. So all sources that are not in the European Union must be at least fair in many respects, because otherwise all the producers inside Europe will play in an unfair business, right?
Well, I think that this with the digital passports and the battery digital passports, I think is the way that this dealing. We open the questions to the floor or the online audience. I don't know if you have Hannah. Wait.
So thank you very much. Can you hear me? Yeah. Thank you very much for these insightful points. And you raised a few things regarding the market, political will, and also the global impact. So I was thinking that while we're already doing stakeholder engagement and we're looking at the market, so what drives change usually is money and political power. So if you can offer employment and at a profitable margin for yourself, obviously the change is going to come fast, but sometimes these interests collide with actually the political will. So what is being done on our level? So we have here academic institutions, research institutions, service providers in different sectors. What can we do to lobby politics at the national and European level to actually support these changes through things like subsidies or incentives being offered to big companies. And as you said, the big companies, they have so much, they play in bigger leagues, so they're not really looking at the resources that are right in front of them. So what can we do to bring about this change without fear scenarios, without being pushed so much by war and pandemics and shortages? And also while reducing our impact, not just in Europe, but the negative impact on supply chain, on traceability. So there are laws about making sure that fast fashion isn't produced on the backs of Bangladeshi workers. So how can we extend this to the raw material sector?
If I could say a short thing, I think we have, Hannah, a first issue is, I think that the European Union is having a huge we have a huge problem, and is having a huge program is the amount of food that we waste. And now is in the next year we are going to face that we are doing things that should not be done. I mean, and then I think they have identified first to work at the social level the issue of the amount of food that we waste. And but I think I will expect that I can imagine not a local level, a Spanish level, for example. I think that it should be something that should be promoted at the European level. Is you mentioned, you raise a question that is having some concerns of the education or an implication of education on the population. I see a long-term basis, but it should be like a directive maybe on that to help.
Yeah, we talked about a lot about regulations. They are definitely a driver. We need to be careful how far we want to push this as a European community. We have to maintain a certain compatibility to other players. But history has shown that if you go sustainable, if you go ESG driven, as an economy, you can be successful. And this is what we need to do. We have Scandinavian countries, they are extremely successful, being sustainable since many, many years. So the right balance between regulations and free market, but going very strictly the sustainable way.
Well, talking about politicians, I must say that I like a lot politics, and I have been really paid attention to the show we got these days in Spain. So I don't know if we can get them involved right now in these issues, but it's true. At least in Spain, we have this program, the PERTE program, that I think the ultimate intention of this program is to get big companies involved in, and we have several programs, and one program is a circular economy. So the idea is to help these companies to promote the circular economy. So I think the governments are doing something to shorten the gap between the true producers or companies that are really in the market and research. So again, I think the point is that, and this is our role as a consultant, is to phone the guys in the company saying, hey, you have an opportunity. You have money, public money, our money at the end, and you have the opportunity to grow in a different market, and yeah, go ahead. But I think this is the real obstacle, that the big companies are not really aware of it, basically because if you have industrial process that works and provides a profit, let's go.
So thanks to all of us. I think yes, that we can talk about opportunities and barriers for hours, but we need to go on. And I think this last step for us, for customers, we need the traceability, sustainability, and all these aspects of increased availability. Thanks to all of you for the interventions.
So thank you very much again to all the speakers and for this interesting discussion. Now we have already reached the end of the technical session of the workshop, and we will now move on the networking lunch that will take place at the terrace of the hotel at the ground floor. And we invite to all of you to join us and take the opportunity to ask further questions for the speakers that presented before. As project manager of stakeholder engagement, we know that that's the moment to the real networking session and to connect with stakeholders. And we would like you thanks you for all attending the workshop organized by as a part of the C4 Value project. We hope you found it interesting, and also I hope you see you again soon. Another time, thank you all the attenders that connected online, and thank you very much for all the speakers that comes to the event and travel to Barcelona to attend that event. Thank you very much to all.